A star is a gigantic nuclear factory that produces light. The one we know best and the one closest to us is the Sun. But there are billions of stars like the Sun in the universe. They shine like the Sun, but we only see them at night. The Sun, on the other hand, is so close to us that its presence during the day dazzles us, and even prevents us from seeing the other stars. Unlike a planet, a star produces its own light. Planets, on the other hand, simply reflect the Sun's light. A star is a gigantic ball of gas millions of times more massive than the Earth, and hundreds of times larger. It spins on its axis, producing intense light. Surface temperatures reach several thousand degrees. There is a wide variety of stars, each different from the next: red, blue, massive, small. Stars emit light because the matter that makes them up is extremely compressed in their center, in what is known as the star's core. The heat in this core reaches several million degrees, producing nuclear reactions and releasing gigantic amounts of energy. This energy is then released in the form of light. Nuclear reactions in the core cause atoms to coalesce and fuse. In the vast majority of stars, hydrogen atomic nuclei fuse to form helium atomic nuclei. Once upon a time, interstellar clouds of gas and dust collapsed under their own weight, giving rise to stars. These giant complexes of molecular clouds appear to telescopes as dark specks, standing out against a luminous background. These systems can reach diameters of up to 300 light-years. They are the most massive structures in the galaxy, independently of globular clusters. And it's precisely where we see dark, cold clouds of gas and dust today that new stars will one day sparkle. Nothing in the universe is eternal. The night sky doesn't look the same today as it did a billion years ago, and it will look very different a billion years from now. The birth of a star can take tens of thousands of years. When a star is born, the gas surrounding it is colored, and irregularly shaped clouds of dust stand out against a glowing background. Within these cosmic nurseries, the space between stars is not empty. Gravitation can bring interstellar material together to form gigantic clouds. At the very heart of these clouds, it's dark and cold. Good conditions for different atoms to combine and form simple molecules, hence the name, molecular clouds. When a dense cloud of interstellar matter contracts and fragments into small clusters under the action of gravity, the center of the cluster forms a protostar. In the same way that the cluster of matter that gave birth to it turned on itself, the protostar is guided by a rotational movement, and the residual matter is distributed in a disk that rotates around it. The protostar attracts matter from the disk, enabling it to continue growing. Dense bursts of gas called jets occur as large quantities of matter fall onto the protostar. These apparent jets reveal the protostar's presence within the opaque clouds. The protostar generates energy by compressing these gases. The denser it becomes, the more matter it attracts, and the greater its gravitational attraction. The movement of matter accelerates, and the temperature rises. Once its core is sufficiently heated for hydrogen to fuse into helium, the protostar becomes a young star. For almost 90% of its life, the star converts the hydrogen in its core into helium by nuclear fusion, producing energy that is released in the form of light. The star's life comes to an end when the fully transformed hydrogen in its core runs out, The star will then die out more or less slowly, depending on its mass. The most massive stars explode in a supernova, ejecting enormous amounts of matter and energy, and triggering the formation of new star nurseries elsewhere in the galaxy. Less massive stars like the Sun begin to swell and gradually transform into red giants. New nuclear reactions begin in its core, and it starts to lose more and more of its gas. The ejection of matter accelerates, forming an envelope known as a planetary nebula. At the center, a white dwarf remains, a dense extinct star. A star's life expectancy therefore depends on its mass and the amount of fuel available to produce its energy. The Sun lives for around 10 billion years and is already halfway through its life, at around 5 billion years. This doesn't mean, however, that the more massive a star is, the longer it will live. Even if it has a lot of fuel, it also burns a lot of fuel, so it will burn out more quickly. This is how a star tens of times more massive than the Sun can have a life hundreds of times shorter. In the celestial panorama, stars may appear to be relatively isolated from one another, but in fact they are not solitary bodies, but come together to form associations and clusters of varying density. In some cases, they form much closer links, forming pairs known as double stars or binary systems, in which the evolution of one star influences that of the other. In the majority of binary systems, the distance between stars remains high. The periods of revolution of one star around the other usually exceed 100 years. The discovery of double stars was one of the first to be made using telescopes. The star Mizar, located in the Big Dipper, was the first to be identified as such. Scientists immediately surmised that Mizar must not represent a unique case, given the sheer number of stars in the universe. In the 1780s, a catalog was published reporting the observation of almost 700 double stars. The biggest problem in the early days of discovery was whether the double stars observed were really related to each other, or whether their association was merely the result of perspective. It was therefore necessary to measure the distance between some of them using the parallax method. Scientists observed that each star followed a complicated ellipsoidal pattern in the sky. These results confirmed that the double stars were physically associated and constituted a binary system, since according to the laws of celestial mechanics, two gravitationally bound bodies follow an elliptical orbit. Double stars are divided into three main categories. There are visual binaries, photometric binaries, and spectroscopic binaries. This classification refers to the way in which the stars are associated. Visual binaries are so named because of their motion relative to another star, presumed to be its companion. Photometric binaries are those that exhibit periodic variations in brightness due to reciprocal eclipses of one star over the other. They are also known as eclipsing variables. Spectroscopic binary stars are known thanks to a stellar spectroscopy technique that uses the Doppler effect of spectral lines to check whether two stars at a close distance are related or not. The Doppler effect is a physical phenomenon whereby an observer moving in relation to a source emitting waves perceives an apparent change in the frequency of these waves. Let's discover some of these double stars. Located in the constellation Scorpius, some 378 light-years from us, is the binary star AR Scorpii. Its main star is a white dwarf about the size of our planet Earth, but 200,000 times more massive. Its companion is not visible. It must be a small, cold red dwarf orbiting with a main star around their common barycenter. AR Scorpii is characterized by unexplained light fluctuations. In fact, when it was first studied, it was mistakenly classified as a variable star. Every minute, its optical flux increases by a factor of 4 in less than 30 seconds, from an apparent magnitude of 16.9 to 13.6. Observations of AR Scorpii since the 1970s suggest that it belongs to a class of stars known as intermediate polars. This class defines spinning white dwarfs that attract and incorporate material from a second, lower mass companion star. The result is an accretion disk. Located around 8,475 light-years away in the constellation Sagittarius, WR-104 is a Wolf-Rayet star. It was discovered in 1998. A Wolf-Rayet star is defined as a hot star with a mass equivalent to several tens of solar masses. During a brief phase following its main sequence, a Wolf-Rayet star expels the matter surrounding its core in the form of very violent stellar winds. The core is then exposed and explodes into a supernova. WR-104 is a binary star accompanied by another OB-type star. Its orbital period is around 240 days, giving their stellar wind a spiral shape, extending over 200 AU. Recent optical measurements of WR-104's rotational axis suggest that when the star explodes supernova, it will emit jets of material from its poles, as well as energetic radiation, and even a gamma-ray burst, which could be dangerous for Earth due to its proximity to the star. The explosion could occur within 300,000 years, giving us plenty of time to confirm this hypothesis. LL Pegasi is a Mira-type variable star located 3,900 light-years from the Sun. Mira-type variables are characterized by very red colors, luminosity amplitudes greater than 1 magnitude, and pulsation periods greater than 100 days. These red giants are in the final stage of their stellar evolution. Within a few million years, they will expel their outer envelope to form a planetary nebula and become white dwarfs. This binary star system includes an extreme carbon star. This type of star develops a chemical composition in which carbon dominates over oxygen. The two stars are hidden by the dust cloud ejected from the carbon star and can only be observed in infrared light. LL Pegasi is surrounded by a spiral-shaped nebula that is considered a protoplanetary nebula. It adopts the unusual shape of an Archimedean spiral, a curve described by a point moving uniformly on a straight line, rotating itself uniformly around a point. This shape may be due to the interaction between the stellar companion and the carbonaceous star. Eta Carinae is a star system composed of at least 2 stars. It's known by its French name, Eta de la Carine. It is incredibly bright, more than 5 million times brighter than the Sun. Eta Carinae is located 7,500 light-years from planet Earth, in the constellation Carinae, within our own Milky Way, It is only 2.5 million years old. The two components, Eta Carinae A and B, are difficult to observe, as a very dense bipolar nebula surrounds them. The nebula is called homunculus. Eta Carinae B orbits eccentrically, completing one revolution in around 5.54 years. Eta Carinae A is a blue hypergiant variable star. Astronomers estimate its diameter to be around 1,150 times that of the Sun, equivalent to about 1.6 billion kilometers. Its surface temperature reaches 40,000 degrees Celsius, or 72,000 degrees Fahrenheit. At magnitude 4, Eta Carinae is easily seen by the naked eye in pollution-free skies. However, its location far in the southern celestial hemisphere makes it invisible to European and most North American observers. Nevertheless, observers in the southern hemisphere, in New Caledonia, or Réunion, for example, can see it rise brilliantly in the sky. It appears to be the brightest star in the large Carina Nebula, between Canopus and the Southern Cross. Through a telescope, Eta Carinae appears distinctly orange, enclosed within the nebula. Eta Carinae underwent an explosion observable from Earth only 150 years ago. The consequence was the formation of the gigantic nebula known as the Homunculus Nebula. It now reaches the size of the solar system. Until the 17th century, there were no reliable records of Eta Carinae. The first accurate observation of the star was made in 1677 by Edmund Halley, but its position was simply indicated in relation to another star within the constellation Charles Oak. The scientists gave it an apparent magnitude of 4, which corresponds to 3.3 on the modern scale. For much of the 17th century, Eta Carinae was not distinguished by its luminosity. In 1827, William Burchell observed the star's unusual brightness. He wondered about the possibility of variations in the star's brightness. At the same time, British astronomer John Herschel made a series of precise measurements from South America and demonstrated that Eta Carinae constantly shone at around magnitude 1.4. But one evening in late 1837, he was surprised to find that the star was brighter than Rigel. This marked the start of a period known as the Great Eruption, which would last almost 18 years. In January 1838, Eta Carinae equaled Alpha Centauri in luminosity. This diminished over the following 3 months. Over the following years, the star's luminosity was regularly observed to rise and fall. In 1895, Eta Carinae's luminosity faded to magnitude 7.5. Its visual dimming is thought to be due to the gas and dust expelled during the Great Eruption. The variations in brightness observed during the eruption are more akin to the behavior of a supernova than that of a massive star releasing its layers before dying. Despite the power of the explosion, however, the star survived. The explosion enabled it to eject its outer layers, but was not sufficient to completely annihilate Eta Carinae. According to some astronomers, this phenomenon can be explained by the fact that the eruption was actually the fusion of two stars. In 2018, a published study proposed a scenario that could explain the events observed during Eta Carinae eruptions. Originally, it could have been a triple system, made up of a tight binary, Eta Carinae A and B, around which a third member, Eta Carinae C, gravitated. These three components would then undergo multiple interactions. As the largest star in the system, Eta Carinae A reached the end of its life. It expanded and lost part of its atmosphere to its companion, Eta Carinae B. A transfer of mass between member A and member B took place. A transfer of mass between member A and member B upset the system's gravitational balance. Eta Carinae A moved away from B, which became much more massive. As it moved away, Eta Carinae A began to interact gravitationally with a third star, Eta Carinae C, which had remained further away from the system. As A tended to move away from the system, C altered its trajectory and moved closer to Eta Carinae B. It eventually merged with this star. It eventually merged with Eta Carinae B, resulting in an extraordinary projection of matter. At the start of the merger between Eta Carinae C and B, the projected matter was dense. They expanded very slowly. At the very moment of fusion, a huge explosion occurred. This created the bipolar lobes of the Homunculus Nebula, which are still in place today. This material caught up with the slow-moving projectiles and pushed them along, heating up the environment. This was the main source of light during the Great Eruption, observed by astronomers from 1837 onwards. While Eta Carinae B and C merge, Eta Carinae A continues to gravitate in its elliptical orbit. It crosses the outer layer of B every 5.5 years, generating shock waves that give rise to X-ray emissions. Eta Carinae's increased brightness is probably due to the dissipation of the dust cloud in our line of sight. This cloud completely surrounds the star and its winds. The light the star emits in the direction of Earth is obscured. As for Homunculus, it can be observed because it is 200 times larger than the dust cloud. According to scientists, around 2032, the dust cloud will have completely dissipated, revealing the stable brilliance of the central star. It will then be possible to study Eta Carinae with precision. The four-component spectroscopic binary system of KIC 7177553 is a particularly interesting and complex structure. Using the Kepler Space Telescope to study the system, two binary stars in orbit around each other in a hierarchical structure in which one of the two systems is an eclipsing binary were revealed. The two binaries each have an accretion disk, which in turn are surrounded by an outer accretion disk. Astronomers became interested in this star system because a study of one of the eclipses revealed variations in eclipse timing, with an amplitude of around 100 seconds and a period of 529 days. This phenomenon suggests that an exoplanet is evolving in an eccentric orbit around this system, which would be a great opportunity to study how planets form and evolve within hierarchical systems. The WISE pair 2150-7520AB is a large binary. Its two members are separated by a large distance. Located 78.9 light-years away in the constellation Octant, this strange binary system consists of two brown dwarfs. They are separated by 341 astronomical units, a record equivalent to 8 times Pluto's distance from the Sun. The system could be between 500 million and 10 billion years old. Prior to this discovery, astronomers did not believe that such a system could remain connected over such a large distance for billions of years, due to the interactions undergone in the galaxy. Zeta Ursae Majoris, translated as Zeta of the Big Dipper in French, is a multiple star located in the constellation of the Big Dipper, the second star from the end of the chariot. Its traditional name is Mizar. Mizar is the star in the middle of the panhandle. To see it with the naked eye, you need good eyesight. With binoculars, however, it's easy to see. Using a higher magnification telescope, it turns into a sumptuous pair of tightly packed white stars. The distance between these two stars is equivalent to 381 times the distance from the Earth to the Sun. Its apparent magnitude is around 2.2. Mizar was the first telescopic binary to be discovered. It consists of Mizar A and Mizar B. The latter, the secondary star, has a magnitude of 4.0 and lies 381 astronomical units from Mizar A. It takes thousands of years for them to orbit each other. Mizar is accompanied by a star faintly visible to the naked eye called Alcor. Also known as 80 Ursae Majoris, it has a magnitude of 3.99. The pairing of Mizar and Alcor has recently been recognized as a true double star. They are also nicknamed the Horse and the Rider. More than a quarter of a light year apart, their individual motions prove that they are moving together. (61 Cygni, also known as Bessel's star, is a system of two orange dwarf stars of spectral class K, of types comparable to the Sun, located in the constellation Cygni. It is characterized by its ultra-fast self-motion within our galaxy. With a magnitude of 5.2, it's easy to see with the naked eye under a clear sky. With the aid of a small telescope, its two components can be easily seen. Both have a beautiful orange-red color and almost the same spectral type. Their difference in brightness gives the impression of slightly different hues. This is due to the fact that they are one magnitude apart. The fainter star appears a deeper red than the brighter one. In addition to being a sumptuous binary system, 61 Cygni is considered to be the star of greatest historical importance. It was the very first star whose distance was assessed using the parallax method. It was in 1806 that astronomer Giuseppe Piazzi noticed that this star was moving rapidly across the sky, implying that it must be rather close to the Earth. Astronomers then investigated whether the star had a slight to and fro motion. This oscillation over a period of 1 year is expected due to the Earth's rotation around the Sun. Nearby stars must change position relative to more distant stars as the Earth traverses its orbit, if we follow the parallax phenomenon. A few years later, in 1838, astronomer Frederick Bessel succeeded in making a precise measurement of the Swan's 61 motion over the course of a year. For the very first time, he was able to estimate the distance to a star. The value he found at the time, 10.5 light-years, was very close to the currently measured value of 11.4 light-years. This discovery confirmed the totally unexpected depth of the universe at the time, 100,000 billion kilometers. (70 Ophiuchi is a binary star in the Ophiuchi constellation, about 17 light-years from Earth. It is known for having one of the shortest periods. In fact, it takes just 83 years for its two limbs to circle each other. The loop is so fast because the two objects are relatively close to each other. Their period of revolution is within a few years of that of Uranus around the Sun. This means that the average distance between the two members is only around 3 billion kilometers. The proximity of 70 Ophiuchi to the Earth means that we can easily distinguish the two components, despite their close proximity. The pair's main star, 70 Ophiuchi A, is a yellow-orange dwarf comparable in size to the Sun. The secondary star, 70 Ophiuchi B, is an orange dwarf much less massive and luminous than its companion. The orbit of 70 Ophiuchi B is eccentric. It can pass within 11.4 astronomical units of 70 Ophiuchi A at its closest, and 34.8 astronomical units at its furthest. Their next maximum separation will occur in 2024. Seen from Earth, this binary star is spectacular, easy to separate, and very colorful. The yellow and orange tones can already be seen through a 60mm telescope. The color of the pair are reminiscent of those of 61 of the Swan. This multiple star system is located in the Lyra constellation, around 162 light-years from the Solar System. Epsilon Lyrae is an exceptional star, consisting of a pair of double stars called Epsilon 1 and Epsilon 2, and is sometimes nicknamed the double-double. Kepler's laws state that the closer the stars are, the faster they rotate around their common center of gravity. However, Epsilon 1 and Epsilon 2 are separated by an abyss estimated at 10,000 times the distance from the Earth to the Sun, so they orbit each other very slowly. Their rotation period is estimated in hundreds of thousands of years. The Epsilon 1 binary system has a rotation period of around 600 years. Epsilon 2 has a rotation period twice as long. The stars in Epsilon 1 have magnitudes of 5.02 and 6.02 respectively, and those in Epsilon 2 have magnitudes of 5.14 and 5.37. Epsilon 1 and Epsilon 2 form a beautiful double star in binoculars, or even with the naked eye. The two double systems look very similar, but are oriented perpendicular to each other. Given the young age of the stars that make up this double-double, they appear very white in telescopes. Observed with an instrument more powerful than binoculars, each of the two components splits, and each system appears as two double stars. Sirius is a binary star system consisting of a main sequence star and an accompanying white dwarf. Also known as Alpha Canis Majoris, it lies in the constellation of the Great Dog, where it is the main star. From Earth, Sirius is the brightest star in the sky after the Sun. A white star, it is located 8.6 light-years from the Sun. Its proximity and luminosity make it one of the most coveted subjects of study for astronomers. From our temperate northern latitudes, Sirius can be seen low above the southern horizon on winter nights, shimmering with a magnificent steel-white glow. It generally glows with turbulence, and on certain nights can show iridescent flashes. Its little companion, which is 10,000 times less bright than the main star, is much more discreet through telescopes. Because of its relative proximity to the Sun, Sirius has its own motion, which means that its position on the celestial sphere varies faster than that of many other stars. Sirius is a binary star made up of two parts, Sirius A and Sirius B. Sirius A, a white main sequence star, is the one we can observe with the naked eye. Its mass is around 2.12 solar masses. It is thought to be around 250 million years old. Sirius A's chemical composition is highly abundant in iron, 3 times that of the Sun. Its surface has a weak magnetic field. Keeping Sirius A company is Sirius B, a white dwarf orbiting with a period of about 49.9 years. Its mass is 1.03 solar masses. The distance between Sirius A and Sirius B varies between 8.1 and 31.5 astronomical units, with an average distance of 19.5 astronomical units. The orbit of their system is particularly elliptical. Although the angular separation between Sirius A and Sirius B is large enough to observe both members, this remains compromised by the contrast in brightness between the two. Sirius B has a much lower brightness than Sirius A. It is warmer and smaller, with a diameter comparable to that of the Earth. The presence of Sirius B has been studied thanks to the study of Sirius A's own motion. As Sirius B was already a white dwarf, it must initially have been more massive than Sirius A, with a mass of at least 6 solar masses. A stellar wind phenomenon stripped Sirius B of much of its mass, making it the least massive star in the system today. Epsilon Aurigae is an eclipsing binary star in the constellation of Kocher. It is also known by the traditional names of Haldus, Almaz, or Al-Ans. It lies around 2,000 light-years away. Its brightness ranges from 3.0 to 3.8 magnitudes over a period of just over 27 years. Spotting it in the sky is no easy task. It is visible in winter in the northern hemisphere, alongside the bright yellow star Capella. It forms the apex of the isosceles triangle that forms the nose of the constellation of the Coachman. An eclipsing binary star system is a binary star in which the plane of revolution of both stars is in the observer's line of sight. The two members therefore periodically eclipse each other. Eclipsing binaries are variable stars in that they darken each other. The visible star in the pair is a supergiant of spectral type, A91A, one of the brightest stars within 1,000 parsecs of the Sun. Its diameter is roughly equivalent to 100 solar diameters. The other member of the pair, eclipsing, cannot be seen. The phenomenon observed during an eclipse is that the level of obscuration of the first star by the companion diminishes rapidly. It's as if a hole remains in the latter. Astronomers have been studying this mysterious star since the 19th century. An eclipse in 2009 and 2010 enabled a team of scientists to study Epsilon Aurigae using a Californian interferometer. The eclipse began in August 2009 and peaked at the end of December of the same year. It persisted throughout 2010 until the star returned to normal brightness in 2011. The images revealed a dust disk 1.5 billion kilometers or 900,000 miles in diameter, equivalent to the distance between Saturn and the Sun, and 75 million kilometers thick. It contained a small massive star. This discovery confirmed a hypothesis, defining Epsilon Aurigae as an atypical binary system. This is the combination of a large low-mass star nearing the end of its life, which is occasionally eclipsed by a star itself wrapped in this large disk of dust. This phenomenon leads to eclipses lasting 18 months. Algol is another eclipsing variable binary like Epsilon Aurigae. It is also known as Beta Persei. Algol is located in the constellation Perseus and has a magnitude of 2. Algol is 92.8 light-years away. Its proper motion is very small compared to its radial velocity. From Earth, it is easily visible to the naked eye. During an eclipse, its brightness gradually diminishes over 5 hours until it reaches minimum brightness. It then regains its initial brightness over the following 5 hours. This change in brightness can be seen by comparing it with the star Almach, or Gamma Andromeda, which is usually as bright as it is, but becomes noticeably fainter during an eclipse. Its character as a variable star means that it slowly changes its brightness every 2 days and 21 hours, but not due to a change in size, as is very often the case with variable stars. In 1783, an astronomer proposed an explanation for this phenomenon of diminishing luminosity. It is caused by an eclipse that occurs every time a small companion passes in front of the main star. Algol was thus discovered as a very close double star called a spectroscopic binary, whose orbital plane lies precisely in our line of sight. Albireo, also known as Beta Cygni, is easily observed by the naked eye at the tip of the Cygnus cross in the constellation Cygnus. When viewed through even the smallest telescope, it is a strong contender for the title of most beautiful star in the sky. A higher magnification will easily distinguish the two stars, which shine with magnificent color. The brighter one has a yellow-orange glow, while the fainter one has a beautiful bluish hue. This majestic appearance has also earned it the nickname Topaz and Sapphire. Albireo is the most contrasting double star available to astronomy enthusiasts, and the fifth brightest star in the Cygnus constellation. The Albireo pair consists of two stars, a yellow star of magnitude 3.1, named Albireo A, and a blue star of magnitude 5.1, named Albireo B. They are separated by 34 seconds of arc, making them visible even with small observing instruments. After many years of discussion about the nature of this pair, it was established that it was a visual binary. A visual double star defines a pair of nearby stars on the sky, whose two stars can be identified separately, using an observing tool such as a telescope. Albireo A is a red giant star of spectral class K32. Its temperature reaches 4,200 degrees Celsius, or 7,600 degrees Fahrenheit. Albireo B is a slightly variable blue star. It is 190 times brighter than the Sun, has a mass equivalent to 3.3 solar masses, and a temperature of 12,000 degrees Celsius, or 21,000 degrees Fahrenheit. Its rotation period is less than 15 hours, making it a fast-rotating star. As a result, it loses part of its mass and is encircled by a disk formed from the same ejected mass. In 1980, astrophysicists thought they had detected the existence of another companion, quite close to Albireo. This companion, called C, is located 46 astronomical units from the primary star. In this sense, it could be a triple system, but this observation has not yet been confirmed. HR 6819, also known as QV-TEL, lies in the Telescope constellation, over 1,000 light-years from the Sun. This binary star comprises a B-type star with emission lines, cataloged as a variable star, and a B3-type star. The pair formed around 50 million years ago. Scientists long believed that the two stars orbited a stellar black hole, forming a triple system. But recently, new data has confirmed that this is a binary system. Between the two stars is a phenomenon known as stellar vampirism, in which one star feeds off the other. The giant star is surrounded by a ring of gas that is the result of the attraction of the smaller star, stripped of its atmosphere. R Aquarii is one of a group of strange binary stars known as symbiotic. It lies around 650 light-years from Earth. As early as the 11th century, its bursts of brightness were noticed. The term symbiotic suggests a particular kind of interaction between stars. It involves a transfer of matter. These stellar duos are extremely rare. They consist of a cold red giant star and a small hot compact star. The dwarf star takes on the atmosphere of the giant star. This loss of matter creates a stellar wind that wraps around the dwarf star. An accretion disk reaching 100,000 degrees Celsius takes shape, and bipolar plasma jets can be emitted. Initially, the binary is in a quiet equilibrium phase, during which the giant star loses energy over a large part of the spectrum. As soon as this equilibrium is disturbed, the binary enters an active phase, with great variations in energy and luminosity, reaching several magnitudes. The star can become up to 750 times brighter than normal. R Aquarii is characterized by a nebula resulting from several major eruptions. Its main star is a Mira-type variable red giant with an effective temperature of 2,600 degrees Celsius or 4,700 degrees Fahrenheit. It is accompanied by a white dwarf star with an effective temperature of 20,000 degrees Celsius or 36,000 degrees Fahrenheit. Their orbital period is 44 years. The giant star is weakened by the upper layers of its atmosphere, which become a stellar wind for the benefit of the dwarf star. This gas evolves in the equatorial plane and also forms a very luminous accretion disk, sometimes accompanied by a bipolar jet. Once the dwarf star has accumulated enough gas, it explodes into a nova. The gas ejected into space forms a bubble on either side of the disk's equatorial plane. A few thousand years later, the dwarf star begins a new cycle of accretion and eruption. A new bubble of gas forms like an hourglass. The dwarf star produces thermonuclear fusion reactions, making its surface 250 times brighter. This cycle continues for as long as the giant star feeds the dwarf star. After this overview of binary stellar systems, let's explore stellar systems with more than two members. Multiple star systems are systems with more than two stars. They can be triple if they contain 3 stars, quadruple if they contain 4, quintuple if they contain 5, and so on. These systems remain smaller than open star clusters, which contain up to 1,000 stars. Modeling a multiple star system is far more complex than that of a double system. The best known are triple systems. They are often hierarchical, i.e., they contain a pair of nearby stars linked to a more distant companion. Today, we know of systems with up to 7 members. Let's take a closer look at what these different systems look like. The Milky Way is populated by over 200 billion stars. Of these, only those that remain close to our solar system are visible to the naked eye from Earth. The closest of these is Alpha Centauri, a complex star composed of 3 stars. It lies 4.37 light-years from the Sun. Also known as Alpha Centauri, it comprises Alpha Centauri A, Alpha Centauri B, and Alpha Centauri C, more commonly known as Proxima Centauri. It is also thought to have at least one planet. Because of its proximity and accessibility, Alpha Centauri is a popular subject of study for astronomers and is one of the most studied multiple star systems. In the southern celestial hemisphere, Alpha Centauri twinkles close to the Southern Cross. As the 3rd brightest star in the sky, after Sirius and Canopus, its brilliance is breathtaking. Its 2 main components form a double star that's easy to observe through a small telescope. The 3rd companion is a little less spectacular, at magnitude 11. Alpha Centauri A and Alpha Centauri B are the 2 main stars. They form a binary star, Alpha Centauri AB. These stars are similar to the Sun. Alpha Centauri A has 1.1 times the mass of the Sun and 1.519 times its luminosity. Cooler and less massive, Alpha Centauri B has 0.907 times the mass of the Sun and 0.445 times its luminosity. The 3rd companion, Proxima Centauri, is a faint, tiny star called a red dwarf. Measuring just 1.5 times the size of Jupiter, it is far less luminous than either of these 2 companions, but holds the record for closest proximity to the Sun, having been at a distance of 4.24 light-years for 32,000 years. Proxima Centauri and Alpha Centauri AB are separated by around 13,000 astronomical units, or 430 times the radius of Neptune's orbit. All 3 stars have their own motion on the celestial vault. Their positions have slowly varied over the centuries. Originally, Alpha Centauri was a double star. The Alpha Centauri AB pair would have adopted Proxima Centauri as it passed close by. Proxima Centauri is therefore gravitationally linked to both stars. HD 188753 is a star system made up of 3 stars, A, B, and C, located 151 light-years away in the constellation of Cygnus. The special feature of this system is that it hosts at least one exoplanet, HD 188753AB. This is the first exoplanet to be discovered in a 3-star system. The components HD 188753B and C orbit each other in 156 days, at the same time as it orbits the 3rd central star, HD 188753A, in 25.7 years, at a distance of 12.3 astronomical units. The exoplanet HD 188753AB orbits the main star. It's a gas giant like Jupiter, but stands very close to its star. HD 131399 is a 3-star star system in the southern constellation Centauri, about 333 light-years from our planet. The system comprises 3 members. The central star, HD 131399A, is a blue star of apparent magnitude 7.08. It is not observable to the naked eye, due to its low luminosity. Accompanying the star is HD 131399AB, a background star that has long been mistaken for a planet. HD 131399A is accompanied by B and C. The latter two form a binary system. Polaris, also known as Alpha Ursae Majoris, is the brightest star in the Little Dipper constellation. It's this star that we call the North Star. It is reputed to indicate with some precision the direction of the celestial North Pole. It has traditionally been used by many civilizations for navigation and has been renamed by many traditional names. Polaris is its traditional name of Latin origin. Its position almost merges with the direction of the Earth's axis of rotation. The other stars in the sky seem to revolve around it. It never appears in the southern hemisphere, and conversely, never sets in the northern hemisphere. Due to the precision of the equinoxes, the North Celestial Pole changes position over hundreds of years. 4,800 years ago, Thuban was the pole star. The star Vega will become one in the future. Polaris is a supergiant Cepheid variable, Alpha Ursae Majoris A, which is accompanied by two smaller stars. Among them, it forms a visual binary with Alpha Ursae Majoris B. They are so close together that the companion was only discovered by its gravitational attraction to Polaris A thanks to photographs taken by the Hubble Space Telescope in 2006. After this overview of triple stellar systems, let's explore quadruple systems, which consist of 4 members. Four Centauri, also known as H Centauri, is a multiple star in the Centaurus constellation. This system is approximately 652 light-years from Earth. 4 Centauri is characterized as a hierarchical, quadruple star system. Its 2 pairs are separated by 14 arcseconds. 4 Centauri A is the primary component. It is a spectroscopic binary, which defines a pair of objects whose orbital motion is detected by the variation in radial velocity of one or more components of the system. Its companion is then detectable by the Doppler effect exerted in the spectrum as it orbits. Only the light from the main star is visible in the spectrum. The visible star is a blue-white subgiant with an apparent magnitude of 4.72. 4 Centauri B is the secondary component. It is also a single-line spectroscopic binary. The apparent star is a white main sequence star. Its apparent magnitude is 8.53. Andromeda is an ancient constellation in the northern hemisphere, identified by the astronomer Ptolemy. Andromeda is visible from our northern latitudes for much of the year. Starting from the square of Pegasus, Andromeda lies slightly to the northeast, identified by its 4 stars, aligned towards Perseus: Alpha, Delta, Beta, and Gamma. It has a long A shape. The large spiral galaxy M31 is the most characteristic object in this constellation, and one of the most famous in the sky. It is known as the Andromeda Galaxy. Of the constellation's 3 dominant stars, 2 are multiple systems. Alpha Andromedae is Andromeda's brightest star. It is also known as Alpheratz or Syrah. On the celestial vault, it represents the head of Andromeda. Gamma Andromedae is a quadruple system, but it's possible that 1 or 2 more distant stars also belong to the system. Also known as Almach or Sadachibia, It lies at the end of the southern leg of the constellations A. It displays contrasting orange and blue colors. Its main star, designated Y1 Andromedae, is an orange giant 80 times larger and 2,000 times brighter than the Sun. It is the brightest component of the system at magnitude 2. Y2 Andromedae revolves around it, and is itself a double star. Y2a Andromedae and Y2b Andromedae revolve around each other in 61 years in a highly elliptical orbit. Both stars are blue, and Y2a Andromedae is itself a double star, with its companion orbiting in just 2.7 days. Mu Draconis is a multiple star in the Dragon constellation. It lies around 85 light-years from the solar system, close to the Dragon's head. Its apparent magnitude is 4.92. Mu Draconis is also known by its traditional name, Alrakis. This quadruple system comprises 4 stars. Mu Draconis A and Mu Draconis B are the 2 main stars. They are very similar yellow-white stars in close orbits. Their apparent magnitude is 5.6. They can be observed with a small telescope under perfect weather conditions. Mu Draconis B is itself a spectroscopic binary. Mu Draconis C, meanwhile, is a red dwarf about 12 arcseconds from its companions A and B. After this overview of quadruple star systems, let's explore quintuple systems, which consist of 5 members. Sigma de Orion, also known as Sigma Orionis, is a star system made up of 5 stars located in the Orion constellation, some 1,150 light-years from our planet. The main component is Sigma Orionis AB, a double star whose 2 members are separated by 0.25 arcseconds. These are rather young dwarfs, only a few million years old. Sigma Orionis A is a blue star with a magnitude of 4.2. It is the brightest of the pair. Sigma Orionis B is a B-type star with a magnitude of 5.1. The pair completes 1 revolution in 170 years at a distance of around 90 astronomical units. The 2 components, A and B, radiate the equivalent of at least 30,000 solar luminosities. They are one of the most massive pairs of visual binaries. They reach masses equivalent to 18 and 13.5 solar masses respectively. Sigma Orionis D and E are just behind the A and B pair in terms of luminosity. They are respectively 4,600 and 15,000 astronomical units away from Sigma Orionis A and B. They are dwarf stars, reaching around 7 solar masses. Sigma Orionis E is referred to as a strange star because of its high helium content. The final component of this quintuple system is Sigma Orionis C. It is close to the AB pair at around 3,900 astronomical units. It is an A-type dwarf star. The orbits of Sigma Orionis C, D, and E are unstable. They may be accelerated by gravitation and expelled from the system long before they die. Also known by its traditional name, Dabi, Beta Capricorni is a quintuple star system located in the constellation of Capricorn, 328 light-years from Earth. It lies close to the ecliptic, the plane in which the Earth orbits the Sun, and can be occulted by the Moon, but also more rarely by the planets. Beta Capricorni is a complex system. With binoculars or a small telescope, it can be mistaken for a double star. The brightest component, Beta Capricorni A, has an apparent magnitude of 3.05. Its fainter component, Beta Capricorni B, has an apparent magnitude of 6.09. Both are separated by at least 21,000 astronomical units. They complete their orbits in around 700,000 years. These two main components are themselves made up of several stars. The most complex structure is that of Beta Capricorni A. It has at least 3 components, and its spectrum is difficult to interpret. A pair of stars dominates. Beta Capricorni AA is a blue-white dwarf with an apparent magnitude of 3.08. Its surface temperature reaches 4,700 degrees Celsius, or 8,500 degrees Fahrenheit. Its luminosity is 600 times that of the Sun, and its diameter 35 times that of the Sun. Beta Capricorni AB1 has an apparent magnitude of 7.20. It is accompanied by another guest, Beta Capricorni AB2, which orbits it with an orbital period of 8.7 days. Beta Capricorni B is the simplest and best-known element. It has large quantities of mercury and manganese in its atmosphere. Beta Capricorni BA is a binary star comprising a giant 40 times more luminous than the Sun, with a magnitude of 6.1. The second companion, Beta Capricorni BB, is around 3 arcseconds away. Other objects, Beta Capricorni D and E, are located in the vicinity of Beta Capricorni, but it is not known at present whether they are simply optical doubles or whether they are actually part of the system. Iota Copiae is a multiple star made up of 5 stars located in the Cassiopeia constellation, 133 light-years from Earth. Its apparent magnitude is around 4.5. Iota Copiae A, the main component, is a white star with an apparent magnitude of 4.61. It is itself a binary whose 2 stars are known as Iota Copiae AA and Iota Copiae AB. Iota Copiae B is a yellow-white dwarf with an apparent magnitude of 6.87. The third and final component is Iota Copiae C, itself a tight binary of magnitude 8.50. Its 2 stars, Iota Copiae Ca, a yellow dwarf, and Iota Copiae Cb, a red dwarf, are separated by just 0.41 arcseconds. The Iota Copiae star system is one of the most beautiful. Of its 5 stars, only 3 are accessible to amateurs. A magnification of 100 times is sufficient to separate them, although observation is more comfortable at 200 times. Iota Copiae A emits a white glow, while Iota Copiae B is blue and orbits the latter. Finally, Iota Copiae C is also blue and moves slowly. A true visual spectacle for astronomy enthusiasts. Also known as a Lula australis, Z Ursae Majoris is a multiple system of 5 stars located 27.3 light-years away in the Big Dipper constellation. Xi Ursae Majoris A and B are spectroscopic binaries. Their main stars, Xi Ursae Majoris AA and AB, each have a low-mass companion, named Chi Ursae Majoris AB, a red dwarf, and Chi Ursae Majoris BB, probably a white dwarf. The two main components, Chi Ursae Majoris AA and BA, form a visual binary star. They are on the same main sequence as the Sun. Chi Ursae Majoris AA is a yellow-white dwarf about 101% the size of the Sun, and 110% as bright as the Sun. Chi Ursae Majoris BA is a yellow dwarf, 78% the size of the Sun, and 67% as bright as the Sun. 10 astronomical units separate these two components, and they take almost 60 years to complete an orbit. This system is enriched by a final object, a brown dwarf, which lies 500 arcseconds from the others. Zeta Cancri is a multiple star system in the constellation Cancer, around 80 light-years from the Sun. It consists of 5 stars. Stars A and B orbit with a period of around 60 years. Component A has an apparent magnitude of 5.7. 2 other components, CA and CB, orbit A and B in 1,115 years, at a distance of 197 astronomical units. The CB member probably consists of 2 stars. After this overview of quintuple star systems, let's explore sextuple systems, which consist of 6 members. The star Castor, also known as Alpha Geminorum, is located in the constellation Gemini. One of the brightest stars in the night sky, it is the second brightest star in the constellation, after the star Pollux, also known as Beta Geminorum. It is 49.8 light-years from the Sun. The traditional names Castor and Pollux were given to these 2 celestial twin stars, hence the name of the constellation Gemini, Gemini meaning twin in Latin. Castor is one of the twin sons of Zeus and Leda. Castor is a sextuple star system made up of 3 pairs of binary stars. The first pair, Castor A, is a spectroscopic binary, with Castor AA as its main star and Castor AB as its secondary star. The second pair, Castor B, is also a spectroscopic binary. The main star is Castor BA and the secondary Castor BB. The third pair, Castor C, is a BY Draconis variable. The 2 stars are Castor CA, the main star, and Castor CB, the secondary star. In 2020, an 18th 6-star system was discovered. It's one of the most astonishing we know of today. TIC 168789840, located 1,900 light-years from Earth in the Eridan constellation. At the heart of this 6-fold system are 2 pairs of eclipsing binary stars. These are pairs A and C. Almost 4.8 million kilometers or 3 million miles separate each of their stars. The stars in each pair orbit their partner within a few days. The 2 pairs also orbit together around their common barycenter. Pair B, located 14.9 million kilometers or 9.2 million miles away, orbits pair AC. In this system, each time a star moves in front of and then behind its fainter companion, an eclipse takes place. As the orbital plane of the stars in TIC 168789840 is in our line of sight, we have the enormous privilege from Earth of watching the stars eclipse their partners. The primary stars in this sextuple system are vaguely brighter and hotter than the Sun. The secondary stars are darker and cooler. Pairs A and C are linked by their proximity. The third pair, further away, could have planets. After this overview of sextuple star systems, let's explore the 7-member septuple systems. To date, only 2 septuple systems have been discovered. Nu Scorpii, translated into French as Nu du Scorpion, is a septuple star system located in the constellation of Scorpio. This hierarchical system is made up of 2 subsystems with 4 and 3 members respectively. Nu Scorpii AB is the first subsystem, comprising 4 stars. 2 stars are located at the center, Nu Scorpii AA and Nu Scorpii AB. A third orbits this pair, Nu Scorpii AC. Nu Scorpii B, the 4th and most distant star, orbits this pair. Nu Scorpii CD is the second subsystem, made up of 3 stars. A pair of stars, Nu Scorpii D, made up of Nu Scorpii DA and DB, orbits the third star, Nu Scorpii C. AR Cassiopeiae is the second septuple system known to date. It lies in the constellation Cassiopeia and comprises 7 stars. The main subsystem, AR Cassiopeiae AB, is a triple system. A little further out are 2 other stars, AR Cassiopeiae C and D, then another pair of stars, AR Cassiopeiae F and G, are nearby. These last 4 are common companions in their own right. Although this overview of multiple star systems seems remarkable, it represents no more than a handful of the systems that populate the cosmos. We now know that they are an important component of our own galaxy, as well as other galaxies in the universe. Multiple stellar systems can experience complex interactions between the stars that make them up. These interactions can influence the orbits of the stars, cause matter transfers between them, and even lead to collisions or star mergers. The gravitational effects of multiple stars can also disrupt the protoplanetary disks that surround stars, affecting the formation and evolution of planets in these systems. The presence of multiple star systems can have an impact on the life and habitability of the planets that surround them. The complex orbits and gravitational interactions between stars can lead to significant variations in environmental conditions, such as luminosity, tides, and gravitational forces, which could have consequences for the stability of planetary orbits in conditions favorable to life. The Wolf 1061 star system is located 13.8 light-years from our solar system. Between the Earth and Wolf 1061, there is no vacuum, quite the contrary. Space, contrary to what many think, is not empty. There is no air, but there are gases, dust, molecules, and atoms. There are also many celestial objects, stars, exoplanets, satellites, comets, pulsars. There would be about 30 stars between the Earth and Wolf 1061. On our way, we will cross a multitude of stars, some of which are the center of a planetary system. Wolf 1061 is not the closest exoplanet to Earth, but it is one of the few exoplanets that seem most likely to harbor life. we will take advantage of our trip to the Wolf 1061 star system to observe several exoplanets that astronomers have already studied in hopes of finding traces of extraterrestrial life. On our way, we will pass several exoplanets that are already candidates for the title of the closest exoplanet to Earth where life exists. First stop, the Proxima Centauri planetary system. Located 4.2 light-years away in the Centaurus constellation, Proxima Centauri is officially the closest star to the Sun. It is also called Proxima Centauri, Alpha Centauri C, or Alpha Centauri C. Proxima Centauri forms with the stellar pair Alpha Centauri A and B, the Alpha Centauri system. Despite its proximity to Earth, Proxima Centauri is not the brightest star in our sky. That title goes to the star Sirius, located 8.6 light-years from Earth, which is only the fifth closest star system to the Sun. If Proxima Centauri is not that bright, it is because it is a red dwarf. Red dwarfs can be up to 1,000 times less luminous than the Sun. And then, its mass is only 1/8 that of the Sun, which explains why Proxima Centauri is so dim. On August 24, 2016, an exoplanet was detected orbiting this red dwarf star, Proxima Centauri b. This is the closest exoplanet ever found. Proxima Centauri b is a rocky planet like the Earth. This exoplanet is located in the habitable zone of the star, although it is 7.7 times closer to Proxima Centauri than Mercury is to the Sun. This is because Proxima Centauri is a red dwarf. It therefore emits less energy and heat than a yellow dwarf like the Sun, or a white dwarf like Sirius. Its habitability zone, i.e., the zone where water could be found in liquid form thanks to temperatures that are neither too cold nor too hot, is therefore closer than the habitability zone of the Sun, in which the Earth and Mars are located. However, studies conducted on Proxima Centauri b to determine if life would be possible there have not had the expected conclusion. Astronomers note that Proxima Centauri b is 250 times more exposed to X-rays than Earth, which would make life as we know it impossible. And even if the planet had an atmosphere, it would not withstand the repeated onslaught of frequent eruptions from the red dwarf Proxima Centauri. However, even though it is unlikely that life would survive on such a planet, some astronomers remain optimistic. There are so many exoplanets orbiting red dwarfs that it is likely that there are forms of life that we do not suspect are doing very well there. We might be surprised by the adaptability of some life forms. In fact, Lisa Kaltenegger and Jack O'Malley James, two researchers from the Carl Sagan Institute at Cornell University in New York State, have published a paper along these lines in 2019 in the journal Monthly Notices of the Royal Astronomical Society. Their argument is well thought out. The Earth, in its infancy 3.9 billion years ago, endured even worse storms than Proxima b is currently experiencing, and yet life was able to resist and thrive. The researchers compared the characteristics of the atmospheres of Proxima Centauri b and 3 other near-Earth exoplanets to those of Earth. They compared parameters such as atmosphere composition and thickness, and compared these results to those of the Earth's atmosphere over the course of its history. Of course, for these comparisons, models were used, since the atmospheres of these exoplanets have never been directly observed, only deduced via the mass or density of the planets. The results of this study indicate that even if the atmosphere of Proxima Centauri b is eroded and devoid of oxygen, the UV radiation at the surface remains below the levels known by the primitive Earth, including during the eruptions of the red dwarf Proxima Centauri. Conclusion: UV radiation is not a limiting factor for the habitability of rocky planets around red dwarfs. In January 2019, about 3.5 years after the discovery of Proxima Centauri b, a second planet was detected, orbiting the star Proxima Centauri. This planet was named Proxima Centauri c. The existence of this exoplanet is not yet confirmed, but it would be a super-Earth, i.e., an exoplanet with a mass between that of the Earth and that of a giant planet. Its mass would be at least 5.8 times that of the Earth, and its orbital period would be 1,928 days, or a little more than 5 Earth years. Proxima Centauri c could also be a mini-Neptune, i.e. a gas dwarf planet with a rocky core and surrounded by a thick atmosphere. Because of its large mass and distance from its star, Proxima c is probably not habitable. Its equilibrium temperature is estimated to be minus 234 degrees Celsius, or minus 389 degrees Fahrenheit. More recently, in February 2022, a team of astronomers using the Very Large Telescope VLT of the European Southern Observatory, ESO in Chile, detected the presence of a third exoplanet around Proxima Centauri. This planet has been named Proxima Centauri d. It would be one of the lightest exoplanets detected to date around a star. The Proxima Centauri planetary system continues to surprise us and to break records. It is not surprising that many teams of astronomers have been studying this stellar system close to our own. The radial velocity technique was used to discover Proxima Centauri d, a very light exoplanet. When a planet orbits its star, it makes it move. This movement modifies the light spectrum that our instruments on Earth capture from this star. An object approaching us is red-shifted, while an object approaching us is blue-shifted. This shift is proof that the star is moving, and that an object is orbiting it. Proxima Centauri d would have a mass equivalent to a quarter of that of the Earth, and it would orbit its star in about 5 days. It is located very close to its star, about 1/10 the distance of Mercury to the Sun. According to the first estimates, it would not be habitable. But this statement should be taken with caution in the absence of information on the presence or absence of an atmosphere that could generate a greenhouse effect. Of the 3 exoplanets discovered around the star Proxima Centauri, Proxima b, the first to be discovered, is the most likely to be inhabited. However, we could not physically go there with our current means of propulsion. Take the example of the New Horizon probe, which travels at a speed of 17 kilometers per second, or 10 miles per second. At this speed, it would take us 78,000 years to reach Proxima b, and yet it is the closest exoplanet to Earth. Astronomers can only imagine what life would be like on this planet if they cannot see it with their own eyes. Like most planets orbiting red dwarfs, it would be in synchronous rotation around its star, and would therefore always present the same face. One could therefore imagine that one side would be immersed in darkness with very cold temperatures, and the other would be constantly exposed to very high temperatures. The liquid water and the life could, on the other hand, develop at the border between these two zones. You will see in the rest of our journey that most exoplanets orbiting a red dwarf are in this configuration because of the tidal effect. Let's continue our journey towards Wolf 1061. Before going further, let's stop at 8.3 light-years from Earth, where the fourth closest exoplanet to our solar system ever detected is located, after the 3 exoplanets of the Proxima Centauri system. This exoplanet has been named GI 411b. It was detected by an international team of astronomers in 2019 at the Hot Province Observatory, thanks to the SOFI spectrograph installed on the observatory's 1.9-meter or 6 feet telescope. The telescope of the Observatory des Hautes Provinces is the one which allowed the discovery of the very first exoplanet in 1995, 51 Pegasi b. For the record, 51 Pegasi b orbits a yellow subgiant, a class of stars brighter than yellow dwarfs but less than yellow giants. It is located 51 light-years from us. At the time, no exoplanet closer to Earth had been discovered. This is not the only record that was broken by 51 Pegasi b. Astronomers also had to create a new type of planets to characterize it, because until then, no gas giant as close to its star had been discovered. 51 Pegasi b is therefore what is called a hot Jupiter. Let's go back to the fourth closest exoplanet to our solar system, GI 411b. In 2019, when it was discovered, GI 411b was the third closest known exoplanet to Earth. But it has since been dethroned by Proxima Centauri d, discovered in 2022. The mass of GI 411b is equivalent to 3 times that of the Earth. It orbits the star GI 411 in the Big Dipper constellation in 13 days and is probably rocky. It is very close to its star, only 0.08 astronomical units away, about 5 times closer than Mercury to the Sun. To discover the exoplanet GI 411b, astronomers looked at the observation of red dwarfs. It is easier to find an exoplanet around a red dwarf. First, because these stars represent 80% of the stars in our galaxy. Second, because their mass, much smaller than that of the Sun, makes them more sensitive to the gravitational influence of the planets orbiting around them, which makes them more easily detectable. This is how the SOFI spectrograph detected the exoplanet GI 411b. By detecting the motions caused by the planet's mass on its star as it orbits the red dwarf. The observations gathered on GI 411b do not lean in favor of a possible life on the surface of the exoplanet. It is very close to its star, and even though red dwarfs are cooler than yellow dwarfs, it is still too close to be in the habitable zone of GI 411. It could be that this rocky planet is more like Venus than Earth. GI 411b is not a novelty for the Hot Province Observatory, which has already detected nearly 200 planets. But it is very interesting because of its proximity to our solar system. The observation of this planet in the years to come, and especially of its atmosphere, will be crucial for the astronomers, who will be able to compare their observations with the characteristics of the planets of the solar system. Thanks to its proximity to the Earth, GI 411b, like the planets of the Proxima Centauri system, can be observed directly. Let's continue our journey in the universe to discover the closest exoplanets to Earth. Not far from GI 411b is the exoplanet Ross 128b, located 11 light-years from our planet. Discovered in 2017, the exoplanet Ross 128b orbits a red dwarf, Ross 128, and was detected with the HARP spectrograph at the La Silla Observatory in Chile. It is the closest exoplanet to Earth that could potentially be inhabited, because the star Ross 168 is a rather quiet red dwarf. Its eruptions are less frequent and less violent than those of other red dwarfs, which would increase the chances of preserving the atmosphere of Ross 128b if it had one. If Ross 128b contained liquid water, it would be much more favorable to the development of life than Proxima Centauri b, which is constantly bombarded by harmful X-rays and ultraviolet radiation. Although the exact mass of Ross 128b is not known, nor its radius, astronomers have deduced that it has a low mass and is therefore probably rocky with a solid surface like the Earth. To complete these assumptions, there are models that can give us hypothetical information about this exoplanet. According to the models, Ross 128b would probably have a mass 35% greater than that of the Earth, and its radius would be 10% greater. It would receive only 38% more light than our planet, and its equilibrium temperature would be rather stable, between minus 60 degrees Celsius and plus 20 degrees Celsius, or between minus 76 degrees Fahrenheit and plus 68 degrees Fahrenheit. Its rotation period would be about 9.9 Earth days, and its rotation would be synchronous. It would orbit 20 times closer to its star than the Earth to the Sun, about 7.4 million kilometers or 4.6 million miles from its star. It is not yet known if it is located in the habitable zone of its star, because everything depends on its characteristics, in particular, on the composition and thickness of its atmosphere. It would most likely be located at the edge of the habitable zone, but nothing is confirmed yet. According to calculations, Ross 128b has a similarity index with the Earth of 0.86, which makes it the third exoplanet with the highest similarity index. The planet with the highest Earth similarity index is TRAPPIST-1b, with an ESI of 0.90, and the second planet is Kepler-438b, with an index of 0.88. But both of these planets are farther away from us, which makes Ross 128b particularly interesting for astronomers. TRAPPIST-1b remains relatively close, but is still 40 light-years away. As for Kepler-438b, it is very distant, about 475 light-years from our solar system. It is difficult at this time to study the characteristics of the atmosphere of Ross 128b because it does not transit in front of its star. To learn more about this candidate for extraterrestrial life relatively close to us, we must wait for the launch of larger telescopes, such as the ELT, the Extremely Large Telescope, built by ESO, and still under construction in the Atacama Desert in Chile. The ELT, but also the James Webb, will be able to analyze the composition of its atmosphere without using the transits method. On the other hand, here is a piece of information that should give you chills. If Ross 128b was inhabited by an advanced extraterrestrial civilization, then it could have observed the Earth in transit in front of the Sun. Potential aliens from Ross 128b know that we are here and have even had time to determine the characteristics of our planet and its atmosphere. Enough to give you a chill. Let's continue our journey into the heart of the universe in search of the closest habitable planets to Earth. YZ Ceti is a multi-planetary system located 12 light-years from Earth, just next to Ross 128b, as seen from Earth. The particularity of this star system is that scientists have discovered 3 Earth-like exoplanets. It is the second closest multi-planetary system to us, after the Proxima Centauri system. YZ Ceti is a red dwarf in the constellation Whale, which cannot be seen with the naked eye from Earth despite its relative proximity. Its mass is 13% that of the Sun, and its radius is 17% that of our star. It is an eruptive or variable star, which means that it undergoes fluctuations in brightness. In other words, its brightness can increase briefly and suddenly due to flares or stellar spots that move as the star rotates. On August 10th, 2017, was announced the discovery of 3 Earth-like exoplanets around the star YZ Ceti. It is also possible that there is a 4th planet. It would then be one of the smallest planets ever discovered. All 3 planets are too close to the star to be in its habitable zone, but they are all similar in size to Earth. According to astronomers' estimates, they would not exceed 1.5 times the size of the Earth. YZ Ceti b is the closest planet to the star. It goes around it in less than 2 days. It is very close to YZ Ceti, only 0.016 astronomical units from its star. For comparison, 1 astronomical unit is the distance between the Earth and the Sun. It is also the least massive of the 3 exoplanets in this multi-planetary system, with a mass of 0.75 times that of the Earth. YZ Ceti c is located 0.021 astronomical units of the star, and it makes the turn in 3.06 days. Its mass is 98% that of the Earth. Finally, the most distant planet from the star among the 3 exoplanets is YZ Ceti d. It is separated from its star by 0.028 astronomical units, and it goes around in 4.66 days. Its mass is estimated at 1.14 times that of the Earth. The 3 exoplanets of the YZ Ceti system were detected by radial velocity with a HARP spectrograph at the La Silla Observatory in Chile, like Ross 128b. It is not yet known if they can be observed from Earth with a transit method. Their observation would be interesting for astronomers to continue to understand the formation of planets, but unfortunately, there is little chance that these exoplanets, very close to their star, are inhabited. Not far from YZ Ceti on the scale of the universe, you can see the exoplanet Luyten b, 3rd planet with the highest similarity index to the Earth, ex Aquio, with Ross 128b. We are 12.2 light-years from Earth. This planet is also called GJ 273b. It is in orbit around a red dwarf, the star of Luyten, and it is a telluric planet. It was discovered at the same time as another planet, which also orbits the star of Luyten, Luyten c. But it is Luyten b that interests astronomers because it falls into the category of super-Earths. Its mass is equivalent to almost 3 times that of the Earth, and it receives only 6% more sunlight than the Earth. It could therefore be habitable. This is what the non-profit organization METI has sought to verify. The acronym METI stands for Messaging Extraterrestrial Intelligence, which could be translated as sending a message to an extraterrestrial intelligence. And indeed, that is the goal of this organization, to seek ways to communicate with extraterrestrials and send them messages in hopes of one day getting a response. In October 2017, the METI organization sent a message to Luyten B in hopes of making contact with a potential extraterrestrial civilization. These, if they receive and understand our message, could respond by 2042. The message that has been sent is at the same time musical, mathematical, and scientific, and it is coded in radio waves to maximize its chances of being understood by an advanced extraterrestrial civilization. The METI organization was contacted by the Sonar Festival of Barcelona, a music and technology festival, to develop a message that would be sent into the cosmos to celebrate the 25th anniversary of the festival. The signal was named Sonar Calling GJ273b. It was sent from the ISCAT transmitter in Tromsø, Norway, over 3 successive days in October 2017. Among other things, it contains a tutorial on basic math and science, explaining physical concepts specific to our civilization, such as radio frequencies or our conception of time. In a way, a practical manual so that the aliens can understand the musical message and respond to us with the same communication process. In addition to the tutorial, the message includes 6 original pieces of music, commissioned by the Sonar Festival, short 10-second pieces of music. You may wonder why the Sonar Festival chose the planet Luyten B, and not, for example, Proxima B, whose habitability is still in question, and which is closer to us. Simply because the star of Luyten is visible from the northern hemisphere, where the transmitter is located. It is therefore more convenient to communicate effectively with potential extraterrestrials. We have now arrived at our destination, about 14 light-years from Earth. You are looking at the Wolf 1061 star system. Before we continue our exploration of the nearest habitable exoplanets to Earth, you need to understand why astronomers are looking for alien life on these exoplanets, and how they go about determining whether or not a particular exoplanet might harbor life. Why are we looking for life on exoplanets when it is very likely that we will never be able to communicate with the life forms that will have been discovered? You may be asking yourself this question, which is quite sensible, because even if a giant telescope allows us to find life on an exoplanet located several tens of light years away, several things could prevent us from entering into communication with this life. These are the same reasons that are given in response to the Fermi paradox, the paradox that wonders why, if there is life elsewhere than on Earth, extraterrestrials have never manifested themselves. First of all, it is possible that this life is microbial, aquatic, or animal, and that it does not understand us. And even if an advanced extraterrestrial civilization is found, its communication processes will be so different from ours that communication may be impossible. It is also possible that intelligent civilizations have existed, but that they did not last long on the scale of the universe. They would have quickly self-destructed because of technology, a nuclear war, or other. Or they have already tried to communicate with us, but we did not understand their signs, because their communication techniques are still too advanced for us. We can imagine dozens of answers to the Fermi paradox. But all we know is that the presence of extraterrestrial life elsewhere in the universe is not yet certain, and that perhaps the Earth is an exception. We also know that if another form of life is found elsewhere in the universe, it is very unlikely to come across another civilization that is as advanced as ours. So why are we looking for life on exoplanets? Not only to make contact with extraterrestrials, but also to better understand the appearance of life on Earth, and to find out if Earth is an exception. Currently, the Earth is an exception in the universe because it is the only known planet that hosts life. But perhaps our place in the universe is not so exceptional. Scientists are also interested in the question of whether life could exist in other forms. The life we know is based on 6 atoms: hydrogen, oxygen, carbon, potassium, nitrogen, and phosphorus. We have not yet observed other types of life, but that does not mean it is unlikely. This is the subject of exobiology, a discipline that imagines what living things based on elements different from ours might look like, using notions of astrophysics, planetology, biology, and chemistry. To find life on exoplanets, astrophysicists will proceed step by step. First, the idea is to detect an exoplanet by the transit method, or by radial velocity. The transit method is the most used method to detect exoplanets, but it has some limitations. The exoplanet HD 209458b, located 159 light-years away, was the first exoplanet to be discovered with this method. When a planet passes in front of its star, which is called transit, we observe a decrease in the luminosity of the star. This decrease in brightness of a few percent is measurable by photometry. The transit method allows us to deduce certain characteristics of an exoplanet: its period of revolution, its radius, and even, with precise instruments like the James Webb, certain elements present in its atmosphere. But this method has its limits. The planet must pass in front of its star to be detected, an event that is actually quite rare on the scale of the universe. For example, to see Venus pass in front of the Sun, we would have to wait a century. Once astronomers have detected an exoplanet, whatever the method used, they will deduce its characteristics to be able to establish if the planet is in the habitability zone of its star. This is called Goldilocks. The goal is to know if the planet can contain water in a liquid state, which is essential for the development of life as we know it. A planet too close to its star would be too hot, and the water would evaporate, and conversely, a planet too far from its star would be too cold, and the water would freeze. The balance is tenuous. You now understand why, while more than 5,000 exoplanets have been discovered to date, scientists are not yet certain that other forms of life exist elsewhere than on Earth. But being in the habitability zone of its star does not necessarily make the planet habitable. We have a good example in our solar system with Venus, often called the twin sister of the Earth. Astronomers say that until 715 million years ago, Venus was quite habitable, with large oceans like on the primitive Earth. In fact, Venus is very similar to Earth, with a similar mass and size, so it makes sense that they would have been similar in their early existence. But today, Venus is uninhabitable, with an average surface temperature of about 450 degrees Celsius, or 842 degrees Fahrenheit, and sulfuric acid rain. 715 million years ago, something caused a massive injection of carbon dioxide into Venus's atmosphere, creating an uncontrolled greenhouse effect that has resulted in the planet's hellish environment today. The profile of a habitable planet would therefore finally be quite similar to that of Earth, a rocky planet with an atmosphere neither too small nor too massive. These characteristics are modulated according to the type of star and the distance between the star and the planet. To confirm whether a planet is habitable or not, astrophysicists will not rely solely on its distance from its star or its surface temperature. They will look for biosignatures, in particular, photosynthetic biosignatures, which the largest telescopes today can detect. Now that you know how astrophysicists determine whether or not an exoplanet is habitable, and why they are constantly searching for an Earth-like habitable planet, we can begin to explore the Wolf 1061 system and its planet, Wolf 1061c. The Wolf 1061 star system is organized around the red dwarf, Wolf 1061, located about 14 light-years from us in the zodiacal constellation of Serpentarius. This star is also known as HIP 80824 and V2306 Ophiuchi. For the record, red dwarfs have the ability to burn up to 400 to 500 billion years, 40 to 50 times longer than our Sun. Around this red dwarf orbits at least 3 telluric planets. Wolf 1061c is the one we are interested in today because it is classified as a super-Earth and is located in the habitable zone of the star Wolf 1061. The star Wolf 1061 was first catalogued in 1919 by the German astronomer Max Wolf. This astronomer had published a list of faint stars that had a high proper motion. The proper motion is the apparent motion of the stars on the sky, as seen from the Earth. Later, the star Wolf 1061 attracted the interest of astronomers for its relative proximity to the Earth. Using the radial velocity method, astronomers discovered a triple planetary system consisting of 3 planets, Wolf 1061, B, C, and D. The habitable zone of the star Wolf 1061 is estimated to be between 0.1 and 0.2 astronomical units from the star. The planetary system of Wolf 1061 consists of 3 known planets. It is not excluded that there are others. These planets were detected by analyzing 10 years of observations of the Wolf 1061 system by the HARP spectrograph at the La Silla Observatory in Chile. The team of astronomers behind the discovery used radial velocity measurements of the star's spectrum to highlight these 3 exoplanets and their orbital periods. Wolf 1061b orbits the star in only 5 days, while Wolf 1061c takes 17.9 days to circle the star, and Wolf 1061d, further out, orbits in 217 days. The mass of Wolf 1061c is estimated to be at least 4.3 times that of the Earth, making it a super-Earth. The mass of Wolf 1061b is closer to that of the Earth because it is estimated to be at least 1.4 times that of the Earth, while the most distant planet is 5.2 times the mass of our planet. The 3 exoplanets of the Wolf 1061 system have masses low enough to be rocky planets, but this remains a supposition since we know neither their size nor their density. If this were the case, they would probably have a solid surface. To be able to determine these characteristics, and to know more about the planets of Wolf 1061, it would be necessary to use the transit method. Even if for the moment no transit has been observed from Earth, astronomers do not give up hope of seeing a transit, because the 3 exoplanets have short orbital periods. The chances of seeing a transit are 14% for planet B, 6% for planet C, and 3% for planet D, according to the team of astronomers from the University of New South Wales in Australia. Of the 3 exoplanets in Wolf 1061, only planet C is considered potentially habitable. Wolf 1061b is too close to its star, and Wolf 1061d is located at the outer limit of the habitable zone. Its habitability remains probable because everything depends on its own characteristics, which could not be observed. But while waiting to know more, it is the middle planet, Wolf 1061c, that interests astronomers. Wolf 1061c has long been considered the closest potentially habitable exoplanet. After the discovery of exoplanets closer to our solar system, it is part of the growing list of the closest potentially habitable exoplanets, along with Proxima Centauri b, Ross 128b, and Luyten b. It is, after Proxima Centauri b, the second potentially habitable planet in a triple planetary system. Wolf 1061c is a super-Earth located near the inner limit of the habitable zone of Wolf 1061. The habitable zone of the red dwarf has been estimated by astronomers to be between 0.11 and 0.21 astronomical units, or at most between 0.09 and 0.23 astronomical units. Wolf 1061c is located at 0.08 astronomical units from its star, thus at the lower limit of the habitable zone. It is called a super-Earth because its radius has been estimated to be more than 1.5 times that of the Earth. Its mass is 4.3 times that of the Earth, and its surface gravity is estimated to be 1.6 times that of the Earth. All these estimates have allowed astronomers to assume that Wolf 1061d should have a density close to or greater than that of the Earth. Other characteristics of Wolf 1061c could be estimated from the astronomers' observations. Its orbital period is 17.9 Earth days, and its equilibrium temperature is about -50 degrees Celsius or -58 degrees Fahrenheit, slightly higher than the equilibrium temperature of Mars. Wolf 1061c receives less than 1% of the Sun's luminosity. All these characteristics are only guesses at the moment, because the observation of Wolf 1061c was made with the radial velocity method. To know more, and to confirm the estimates of the astrophysicists, it would be necessary to observe a planetary transit. The method of transits would give us a more certain estimate of the radius, and thus of the density of the planet. We could then know if Wolf 1061c is an ocean planet or not. Because it is very close to its star, Wolf 1061c is certainly in synchronous rotation. As we saw at the beginning of this journey with the exoplanet Proxima Centauri b, it is indeed very likely that there is a tidal effect that makes the planet turn on its axis at each revolution around the star. This tidal effect would be explained by its proximity to its star, Wolf 1061. The planet Wolf 1061c would therefore always present the same face to its star, and could therefore harbor life only in the zone of separation between the diurnal face and the nocturnal face. This fictitious line between the illuminated zone and the zone perpetually plunged into darkness is called terminator. Unless the atmosphere of Wolf 1061c is thick enough for there to be a heat transfer from the day hemisphere to the night hemisphere. If Wolf 1061c were in our solar system, it would be too hot to harbor life because of its proximity to its star. But Wolf 1061, which is a red dwarf, is much cooler than our Sun. For comparison, its surface temperature is about 3,030 degrees Celsius, or 5,480 degrees Fahrenheit, while the surface temperature of our Sun is around 5,530 degrees Celsius, or 10,000 degrees Fahrenheit. Wolf 1061c is therefore well and truly in the habitable zone of its solar system. But to know if Wolf 1061c harbors life, it would be necessary to study its atmosphere. Being in the habitable zone is not enough for life to develop on a planet. As we have seen, the example of Venus is enough to understand that a planet can be rocky like Earth and located in the habitable zone of its star, but have characteristics that make life impossible. Astronomers have estimated that life could have developed on Venus for about 3 billion years because the planet's climate was then stable and temperate like Earth's, between 20 and 50 degrees Celsius, or 68 and 122 degrees Fahrenheit. But about 700 to 750 million years ago, a cataclysmic event caused a massive release of carbon dioxide into Venus's atmosphere, a gas that had previously been trapped in the planet's rocks. Some researchers believe that this event resulted from the strong volcanic activity of Venus. The result? An intense greenhouse effect and rising temperatures that have reshaped 80% of Venus's surface. Today, the planet that was considered as the twin planet of the Earth has an average surface temperature of 450 degrees Celsius, or 842 degrees Fahrenheit, and is considered as the hottest planet in our solar system. Venus was the victim of a runaway greenhouse effect. Heat became trapped in the atmosphere, and the planet became too hot for any form of life. Researchers estimate that during the 3 billion years that the planet was habitable, its landscape strongly resembled those of the primitive Earth, with lakes and oceans. These oceans eventually evaporated because of the heat, which only increased the surface temperature of Venus, since water vapor is a real heat trap. A vicious circle that has shaped the planet we know today, often referred to as an iron planet. In the same way as Venus, if the atmosphere of Wolf 1061c is rich in greenhouse gases, it could be too hot for it to be habitable, even if it is rocky, with characteristics close to those of the Earth, and is located in the habitable zone of its star. Stephen Kane, an astronomer specializing in exoplanets at San Francisco State University, and his team have studied the question of the habitability of Wolf 1061c. According to them, the climate of this exoplanet is rather chaotic. On Earth, climatic changes occur at a rather slow pace, since the Earth's orbit lasts 365 days. But on Wolf 1061c, which orbits its star in only 18 days, these climatic variations would be much faster. The frequency of freezing or warming would therefore be very fast. Imagine living on a planet where it is successively very hot and very cold, without transition. That said, astronomers are still waiting for more data on the planet's atmosphere to be able to make a statement. It is possible that the very short periods of freezing are sufficient to cool the planet, but it would be necessary to push the observations even further to confirm one of these hypotheses. Moreover, according to Stephen Kane and his team, because it is located very close to its star, it would be quite possible that Wolf 1061c, like Venus, experiences an uncontrolled greenhouse effect. There is, however, another argument in favor of the planet's habitability. Like Ross 128, the star Wolf 1061 is particularly quiet for a red dwarf. Most red dwarfs are very active and are prone to superflares that would destroy any life on nearby planets. Especially since red dwarfs are cooler than yellow dwarfs like our Sun, planets orbiting red dwarfs are located much closer to their star than the planets in our solar system. Scientists are not yet sure that Wolf 1061c harbors life. We have too little information to say with certainty that this exoplanet relatively close to our Earth is a paradise, a hell, or something in between. Let's assume that Wolf 1061c is potentially habitable. So what would life be like on this exoplanet, 14 light-years away from our solar system? Many researchers claim that humans could not live on this planet. It's true that planets within a star's famous habitability zone are likely to contain liquid water, one of the prerequisites for the development of an advanced civilization like ours. But researchers believe that in the case of Wolf 1061c, the development of life similar to the one we know would be very complicated. The living conditions for humans would not be pleasant, with a gravity 1.6 times greater than that of the Earth. In addition, its synchronous rotation implies that there is a side of the planet perpetually plunged in the dark, with very low temperatures, and another side without ever nights, with very high temperatures. Humans might be able to survive in the middle zone, the terminator, but they would not live comfortably there. And it is unlikely that in these conditions a species similar to ours, the result of evolution and adaptation to our terrestrial environment, would have been born. But this does not exclude other types of animal or plant species. The question that also arises is that of the conditions of life on a planet orbiting a red dwarf. The synchronous rotation and its two opposite hemispheres are not the only obstacles to the development of a species, such as man, on the planet Wolf 1061c. Living next to a red dwarf is not easy. These stars are known for their frequent eruptions, which emit UV and X-rays, dangerous for human life, and for that matter for all forms of life. The surroundings of a red dwarf star are therefore not a very hospitable environment. Yellow dwarfs like our Sun can have outbursts of anger, like red dwarfs. But in addition to being less frequent, they are less dangerous because the planets orbiting a yellow dwarf are more distant than those orbiting a red dwarf. The Earth is far enough from the Sun not to fear possible eruptions, and we are protected by the magnetic field and by our atmosphere. Planets orbiting red dwarfs are too close, and even if they have an atmosphere, it can be torn apart by the onslaught of stellar flares. Scientists believe that there is a cumulative effect. That is, the more flares there are, the more the atmosphere is torn apart, regardless of the violence of the flares. So yes, recent studies have found that red dwarf eruptions are not as energetic as has been thought for years. Researchers may have overestimated the violence of red dwarf flares. But if the cumulative effect exists, it is the frequency and not the violence of the eruptions that is dangerous. However, not all astronomers are pessimistic about the possibility of life developing in the orbit of a red dwarf. Red dwarfs represent 3/4 of the stars in the Milky Way, and we have already discovered many that are surrounded by rocky Earth-like planets. What would be strange is that among all these planets, which are so many possibilities for the emergence of life, there is not a single form of life that is developed. Other factors may affect the habitability of a planet located near a red dwarf. The characteristics of its atmosphere, its thickness, its liquid water content, the interactions between the magnetosphere and the ionosphere with stellar winds. If the right factors are present, an exoplanet of a planetary system organized around a red dwarf could be habitable by creatures other than humans who would resist other conditions. Moreover, the case of Wolf 1061c is promising, since Wolf 1061 remains a rather quiet red dwarf, with relatively low power and infrequent eruptions. Suppose there were life on the planet Wolf 1061c. The conditions for life would be very different from those on Earth. Imagine a world where there are only days or only nights, depending on where you are. The years would also be shorter, since Wolf 1061c orbits around its star in only 18 days. A year would last barely 3 Earth weeks. Because Wolf 1061c orbits a red dwarf, and not, like the Earth, a yellow dwarf, the landscapes would also be very different, as well as the luminosity of the planet. Our Sun emits yellow radiation, but red dwarfs emit a reddish radiation. The inhabitants of Wolf 1061c would still have a red star above their heads, and the stellar disk would be larger than that of the Sun, since the red dwarf is closer to Wolf 1061c than the Sun is to the Earth. It is possible that there are plants on Wolf 1061c because plants have a photoreceptor for red light, phytochrome, a blue-green pigment found in plant cells. However, the plants on Wolf 1061c would be very different from terrestrial plants, whether in terms of flavor, smell, or appearance. They would probably be black to better absorb the red light emitted by the star. You may find it difficult to imagine a flourishing life but limited to a small strip in the middle of the planet. This is normal. This representation is very far from what we know. But the good news is that if there is life on Wolf 1061c, it is not necessarily limited to the terminator if the atmosphere has the right characteristics. For a very long time, astronomers believed that life on synchronously rotating planets was only possible in the terminator zone. They also thought that for heat transfer to be efficient enough from the day side to the night side, the atmosphere would have to be so thick that it would prevent photosynthesis. It was also thought that such planets would experience high winds and torrential rains all the time, making any complex life forms unlikely. Here is what life looked like according to these assumptions. There are no humans, but plants can survive in such an environment. They can adapt to the constant winds, for example, by anchoring themselves in the ground with their roots, or by developing flexible and unbreakable leaves and branches. There are also animals which communicate by infrared rather than by cries and smells as on Earth, because storms make this type of communication impossible. Underwater life is protected from strong winds and eruptions by the water, and is supported by vast blooms of plankton and black photosynthetic algae. A plankton bloom is when phytoplankton multiply in an ocean. On Earth, this phenomenon has been demonstrated in the depths of the Arctic Ocean and under the sea ice in Antarctica. We can see it forming like a green sheet from space. This phenomenon can only occur if two elements are combined: nutrients and light from the star. We can therefore imagine that these forms of underwater life would develop in the oceans of the illuminated hemisphere of Wolf 1061c. Further studies were conducted from the late 20th century onwards with promising results. Astronomers are now a bit more optimistic about the emergence of life on this type of exoplanet. Studies conducted at the end of the 1990s by NASA researchers have shown that the atmosphere of a planet, if it does contain the greenhouse gases CO2 and H2O, only needs 100 millibars, or 10% of the Earth's atmosphere, for the heat of the star to be transported to the night side. This figure is reassuring because it shows that photosynthesis could then take place. Other studies have shown that in the night side, seawater can circulate efficiently without freezing if the ocean basins are deep enough for the water to circulate under the ice cap. In other words, one could very well find underwater life in a synchronously rotating ocean world, even on the night side. A 2010 study estimated that ocean temperatures would not fall below -33 degrees Celsius or -27 degrees Fahrenheit in the hemisphere perpetually immersed in night. For the difference between the day and night side to be minimal, there would have to be clouds. If Wolf 1061c has clouds, then astronomers agree that this greatly increases its chances of being habitable. Wolf 1061c could be an ocean planet. Maybe you have a hard time picturing what this type of planet looks like. Scientists describe them as a planet that would be covered with an ocean or water over its entire surface. The depth of this ocean could be several tens of kilometers, but this type of planet remains hypothetical. For the moment, we can only think about the hypothesis according to which Wolf 1061c would be entirely covered with water, without really any evidence to confirm or deny this hypothesis. If Wolf 1061c were an ocean planet, it would be covered with high-pressure and high-temperature oceans. To date, astronomers do not know if this environment would be conducive to biological chemistry. What we do know is that if the oceans of Wolf 1061c were to support life, it would certainly be different from the underwater life found in our terrestrial oceans. We know that the oceans are capable of wonders. The origin of life on Earth remains mysterious, but the most likely hypotheses agree that it was born in our oceans, or at least in water. Underwater life can survive extreme conditions. On Earth, we have found living organisms capable of developing in the Dead Sea. The tardigrade is the best example of an ultra-hardy species that can survive incredible pressure conditions. This 8-legged animal, which can grow to just over 1 millimeter, can withstand temperatures ranging from -273 degrees Celsius or -460 degrees Fahrenheit to +150 degrees Celsius or 300 degrees Fahrenheit, but also X-rays, to which it is 1,100 times more resistant than humans, and pressures 4 times greater than those of the deepest ocean. It can also resist to the lack of oxygen or to the isolation because it reproduces alone. It is cryptobiosis that allows it to be so resistant, a state in which it reduces its metabolic process to 0.01% of normal, so that it is almost dead, but not quite. It can remain in this state for decades and rehydrate to wake up at any time. It is therefore quite possible that living organisms of this type can be found on planets like Wolf 1061c, where conditions are less mild than on Earth. There is still much to discover about the secrets of the exoplanet Wolf 1061c. There are many rocky planets in our galaxy, but some of them are located tens or hundreds of light years away from us. Wolf 1061c is one of the most promising because it is close to Earth. The next step to establish an ever more precise portrait of this promising exoplanet is to observe its transit. The transit method will provide crucial information to better understand this planet and determine if it may contain life. When Wolf 1061c passes in front of its star, it will cause a decrease in brightness at Wolf 1061. Scientists will then be able to analyze this difference in brightness to deduce the composition of its atmosphere. The higher the orbital period of an exoplanet, the more difficult it is to apply the transit method, because transits are rarer. In the case of Wolf 1061c, the orbital period is short, which suggests that a transit will be observed rather quickly. Moreover, when the transit method is applied to discover an exoplanet, it is necessary to have observed several transits to conclude that there is a planet in orbit around the observed star. The transit method provides information such as the radius and density of the exoplanet. Astronomers know the spectrum of the star, so they can derive the value of its radius. The relative decrease in the luminosity of the star during the transit is equal to the square of the ratio of the radius of the exoplanet to that of its star. This calculation allows to obtain the radius of the exoplanet. By confronting the radius to the mass, we then deduce the average density. The transit method also provides information on the chemical composition of the planet's atmosphere, as well as its temperature. To do this, astrophysicists measure the spectrum of the star without transit, then with, to deduce the spectrum of the exoplanet. The James Webb Telescope, which was launched in December 2021, will greatly help scientists learn more about Wolf 1061c, its unique characteristics, and whether or not it harbors life. The Space Telescope carries several instruments that allow it to see in the near and mid-infrared. Moreover, in August 2022, the scientific community announced that James Webb had detected the presence of CO2 in the atmosphere of an exoplanet for the first time. This exoplanet is WASP-39b, a gas giant the size of Saturn. It was one of the first exoplanets examined by James Webb from July 2022, and there is no doubt that Wolf 1061c is on the waiting list. Even more impressive, the telescope was able to detect, in addition to CO2 water vapor, carbon monoxide, sodium, potassium, and sulfur dioxide. The detection of this last compound has highlighted a photochemical phenomenon observed for the first time on an exoplanet. The James Webb Telescope is not the only one to be promising. The extremely large telescope of ESO, the European Southern Observatory, should be completed and put into service in 2028. This telescope, currently under construction in the Atacama Desert in Chile, will be the largest ground-based telescope ever built, with a main mirror 39 meters in diameter. For comparison, the James Webb Telescope orbiting the Sun, 1.5 million kilometers or 930,000 miles from Earth, has a mirror 6.5 meters or 21 feet in diameter. The European Southern Observatory's Very Large Telescope has already demonstrated its capabilities by discovering barium in the atmosphere of the exoplanets WASP-76b and WASP-121b in October 2022, the heaviest element ever found in the atmosphere of an exoplanet. So, imagine what the ELT's capabilities will be. This super powerful telescope, when completed, will stand 3,000 meters or 10,000 feet above the Earth and will capture 100 million times more light than the human eye. Let's start at the beginning. What is an ocean planet? When we talk about ocean planet, ocean world, oceanic planet, ocean world, panthalosic planet, aquaplanet, or aquatic world, it is the same thing. All these terms refer to the theoretical model of the ocean planet. For a long time, the idea that there could be planets entirely covered by an ocean seemed like science fiction. For the average observer, ocean worlds were the fruit of the imagination of authors, scriptwriters, and storytellers. But scientists have been seriously considering this idea since the discovery of exoplanets. The discovery of the first exoplanet was announced on October 6, 1995, by Michael Mayer and Didier Queloz. It was named 51 Pegasi b. This Jupiter-like gaseous exoplanet is uninhabitable and very far from us, at a little more than 50 light-years. But its discovery was still a bombshell in the scientific community, because it showed us that yes, there may be other planets in the universe than those of our solar system. Since this discovery, scientists have developed models to describe all types of exoplanets in the universe. Among these models, that of the ocean planet is one of the most intriguing. An ocean planet would be a super-Earth covered with a huge liquid ocean, not necessarily salt water. A super-Earth is a telluric planet like the Earth, but with a mass greater than that of our planet. Watery planets could be 6 to 10 times bigger than the Earth. The oceans of these planets could be very deep, about 100 kilometers or 60 miles according to the models, or even more. Schematically, an ocean planet that moves closer to its star would become a sauna planet because it would be enveloped in a thick atmosphere of water vapor, while an ocean planet that moves away from its star would become an ice planet. Ocean planets could therefore be ice planets that would have migrated towards their star and whose ice would have melted on the surface, thus creating an ocean. In April 2020, a paper by geobiochemist and astrobiologist Donald M. Glaser and his team was pre-published on the ARXIV Open Archive. This article distinguishes two types of ocean planets. The so-called pelagic planets have between 0.2 and 1% of their mass in the form of surface water. For a planet of terrestrial mass, this is equivalent to between 8 and 40 times the terrestrial oceans, enough to submerge the entire Earth. Pelagic planets are to be distinguished from oceanic worlds, which have more than 1% of their mass in the form of water on the surface. This allows for an ocean deep enough to form a layer of high-pressure ice between the rocky crust and the liquid water. You may wonder why ocean planets remain theoretical. It is true that several discovered exoplanets have conditions that are conducive to the presence of liquid water on the surface. But current technologies do not allow us to directly observe whether or not there is liquid water on the surface of an exoplanet. Only atmospheric water vapor can be detected. It is then an indication of the presence of liquid water on the surface, without confirming it at 100%. If ocean planets fascinate us, it is first of all because we thought for a long time that they existed only in the imagination of science fiction authors. And now, astrophysicists tell us that they do exist in the real world. One of the most famous ocean planets in fiction is Camino in the Star Wars series. Camino is the planet where the clone troopers come from, and where the clone troopers train. It is located beyond the outer rim, near the satellite galaxy called Rishi's Daedalus, and orbits the star Camino. Camino is entirely covered in water, but it is home to an intelligent species, the Kaminoans, who supply clones to the Galactic Republic. The ocean planet Camino can be seen in the movie Attack of the Clones. In the series, the planet was previously covered in ice. During various events, the glaciers suddenly melt, creating a watery planet. In the movie Interstellar by Christopher Nolan, released in 2014, there is also an ocean planet, the planet Miller. This watery planet is one of 3 planets orbiting the supermassive black hole, Gargantua. In the movie, the astronauts are tasked with checking to see if any of these 3 planets are habitable. They discover that the planet Miller is under a strong gravitational influence because of its proximity to the black hole, which produces gigantic waves of 1,200 meters or 4,000 feet high. Black holes are very dense regions of space, which contain an immense amount of matter. Their gravitational field is so immense that they absorb all matter, including light. Supermassive black holes have a mass equal to or greater than 1 million times that of the Sun. Beware, Interstellar remains a fiction. According to astrophysicists, a planet in orbit around a supermassive black hole would be uninhabitable. In the case where there would be an accretion phenomenon, that is to say, that the black hole would capture matter with the effect of gravitation, such a planet would be exposed to very hot radiation. It is therefore very unlikely that this planet contains liquid water, and even less likely that it is an ocean planet. In the case where there would be no accretion phenomenon, one could imagine that it is the cosmic microwave background, a radiation emitted 380,000 years after the Big Bang, which would constitute the main source of energy of the planet. According to the principle of relativity, 1 hour on the planet Miller corresponds to 7 years on Earth. This time dilation would allow a planet orbiting a black hole to receive enough heat for liquid water to appear, but the planet would then be too exposed to ultraviolet radiation. Even if it is possible for a planet to orbit a black hole, that world would certainly be very inhospitable. Whether realistic or not, ocean planets fascinate and have fueled the imagination of many science fiction authors and screenwriters. In the early 2000s, Christophe Sotin, a planetary scientist from Nantes, calculated the conditions for the existence of an ocean planet. In other words, he calculated the temperature and pressure conditions under which a planet, which would have been formed at the margins of its solar system, and then would have migrated close to its star, could be covered with water without emerging rocks. The conclusion has delighted science fiction fans. Even if these conditions are locked in relatively narrow limits, they exist. The ocean planet model was initially proposed by the New Zealand astronomer David J. Stevenson of the California Institute of Technology, Caltech, at the turn of the 21st century. This model was then further developed by the team of Christophe Sautin, planetologist and professor at Nantes University. At the origin of the discovery of ocean planets, there is the phenomenon of planetary migration. We speak of planetary migration when a planet moves closer to its star after its formation. This theory was developed to explain the discovery of gas giants too close to their star to have formed there. The first ocean planet was discovered by calculation on December 16, 2009. It was named GJ1214b, or Gliese 1214b, and is located in the constellation of Serpentarius at about 40 light-years from the Sun. We will explore this ocean planet a little later in this trip. But then, how did astronomers come to the conclusion that the ocean planets of science fiction could really exist? Since the middle of the 20th century, even before the discovery of the first exoplanet, important discoveries have been made concerning the presence of water in the universe. In particular, scientists looked at the moons of Jupiter and Saturn. In the 1970s, NASA scientists became interested in Ganymede, a moon of Jupiter, where they suspected the presence of a thick underground ocean sandwiched between two layers of ice. Lewis's work showed in 1971 that radioactive decay could, especially in the presence of ammonia, produce underground oceans in large moons. The search for water on Mars has also been the subject of numerous studies and space missions. Since the first exoplanet was discovered, astronomers are now looking for evidence of liquid water beyond our own solar system. In 2004, Alain Leger, a researcher at the Institute of Space Astrophysics, calculated with his team that a small number of icy planets formed on the outskirts of their star could migrate inwards by up to 1 astronomical unit, the distance between the Earth and the Sun. This migration would melt the ice of the outer layers, forming ocean planets. Today, the existence of ocean planets is no longer a simple scientific hypothesis. Observations from the Hubble telescope, as well as information gathered by space probes such as Galileo, Pioneer, Voyager, or Cassini-Huygens, indicate that several bodies in the universe could harbor liquid water under an insulating shell of ice. But not only. Because the model of the typical ocean planet can vary depending on multiple factors, including the composition of the atmosphere. In June 2020, NASA scientists asserted, based on numerical models, that it is likely that ocean exoplanets are common in the Milky Way galaxy. The first potentially habitable ocean exoplanet was discovered just recently, in June 2022, by the Transiting Exoplanet Survey Satellite. It was named TOI 1452b. Like Gliese 1214b, we will explore it later in this trip. In the meantime, we will discover why ocean planets interest scientists so much. We now know that ocean worlds most certainly exist, even though there is no direct evidence for their existence. Why has this discovery been so important to the scientific community? What is it about these entirely water-covered planets that interests astronomers so much? According to Li Zhang, a researcher at Harvard University, and his team, who classified the exoplanets according to their radius, 1/3 of the known exoplanets are ocean planets. They would thus be billions in the galaxy, and more than 1/3 of the exoplanets discovered would be covered with half water. The Earth is not the only blue planet in the universe. This is good news for astrophysicists who are looking for extraterrestrial life. Astronomers Raphael Luque, a postdoctoral researcher at the University of Chicago, and Enric Palais of the Institute of Astrophysics of the Canary Islands and the University of La Laguna have published an interesting paper in the journal Science. Their study focused on the occurrence of ocean planets around M-type red dwarfs, the most frequent stars in the universe. The conclusion of the study showed that ocean planets are surprisingly frequent around stars of this type. The search for oceanic worlds is important for the search for extraterrestrial life, because water is the origin of life, at least on our planet. This is why NASA is taking a close interest in Europa and Enceladus, icy moons of Jupiter and Saturn. Geysers have been observed on the surface of these moons. The objective of the next exploration missions will be to find molecules of biological origin in the particles spewed by these geysers. It is already known that these two moons have an ocean under an ice pack, and that they are subject to strong tidal forces that cause volcanic activity. This volcanic activity could imply the existence of hydrothermal hotspots at the bottom of these icy oceans. On Earth, these hot springs are home to many forms of life. In the absence of sunlight, it is chemosynthesis that allows living organisms to develop there. Let's look at this in more detail so that you can better understand why, like the icy moons Europa and Enceladus, the ocean planets are of interest to scientists. Water and energy are two essential criteria for the development of life as we know it. Ocean planets already contain water, so it is not surprising that they interest astrophysicists in search of an extraterrestrial life form. Especially if these ocean planets are located in the habitable zone of their star, i.e., neither too close nor too far away, so that the temperature, gravity, and pressure conditions are optimal. If it is proven that an ocean planet does contain water in a liquid state, all that remains is to determine a source of energy. The energy released by the planets in the form of heat can come from two sources: the tidal force or the decay of radioactive materials that compose their mantle and crust. The tidal force depends on the elongation of the orbit of the exoplanet. The decay of radioactive materials depends on the mass of its mantle and the age of the planet. Hence the importance, in order to refine the models, of being able to determine with precision the characteristics of the potential oceanic exoplanets observed. And then, is water and energy sufficient for the emergence of life? Planets can evacuate the heat produced by the tidal force or by the decay of radioactive materials via volcanism and tectonics. For a planet to be habitable, It must therefore have volcanic or tectonic activity, but not too much either. Let's get back to Li Zhang and his team. This researcher from Harvard University has used analyses from the European Space Agency's Gaia satellite to develop a new system for classifying exoplanets based on the constant RT for Earth radius. This new model makes it possible to explain the relationship between the mass, the radius, and the composition of exoplanets. A real step forward to better understand their formation and predict ever more accurate models. This new model shows in particular that the formation and the internal structure of planets are constrained by their dimensions. According to the system developed by Li Zhang and his team, planets with a radius of less than 2 RT are rocky and poor in water. Planets with radius between 2 and 4 RT are water-rich ocean planets. Between 4 and 10 RT, they are planets rich in gas. Beyond a radius of 10 RT, they are gas giants, composed mainly of hydrogen and helium. Li Zhang and his team have put forward an interesting hypothesis to explain the formation of ocean planets. These planets would have formed like gas giants, but would have eventually evolved differently to become water-rich planets. They are at the limit between a super-Earth and a gas giant, with a mass 8 to 10 times greater than that of the Earth. Ocean planets are numerous, but they are not all habitable. This is where the challenge lies in order not to get lost in endless research. We must know how to distinguish between those that are potentially habitable and those that are not. Ocean planets are interesting for scientists looking for extraterrestrial life, but not only. Even if they are not habitable and do not harbor life, they remain objects to be studied because they provide clues about the formation and evolution of planets, and thus of our solar system. Fasten your seatbelt. We are now going on a journey to the very heart of the ocean planets. What can you expect on this journey? Are the ocean planets similar to Earth? According to studies and models, ocean worlds would not be quite like the Earth, or even like Camino in Star Wars, but rather like the moons of Jupiter and Saturn, Ganymede, Europa, and Enceladus. Let's briefly recall the methods used by scientists to detect exoplanets, and therefore ocean planets. Exoplanets can be detected via the transit method, or via the radial velocity method. The transit method consists in detecting variations in the luminosity of a star when the planet orbiting it passes between the star and the observer. This is called a transit. The transit method allows us to deduce the radius of the exoplanet. The radial velocity method is the one used by the James Webb Telescope. This one embeds a spectrograph, which can highlight a Doppler effect. The Doppler effect is the apparent change in the frequency of a sound, or electromagnetic signal, from a moving object received by a fixed observer. This method measures the oscillation of a star in response to the gravitation of an exoplanet, as the star moves towards or away from us. It works whether there is a transit or not. But if there is a transit, it is always better. This method would then allow us to determine the mass of the exoplanet, its radius, and therefore its density, which allows us to deduce its composition. Valuable information to detect ocean planets. These methods allow us not only to detect exoplanets, but also to know if they are gas giants or rocky planets. The observation of potential ocean planets with these methods has shown us that there would be a typical structure for ocean planets, which would be similar to that of the Jovian satellite Ganymede. Ocean planets would be composed of a core of iron, a mantle of ice and rocks, and a surface ocean, salty or not. How is an ocean planet formed according to scientists' models? Let's go back to the beginning of our solar system to better understand the mechanisms of formation of these aquatic worlds. The formation and evolution of the solar system is described by the model of the solar nebula hypothesis, developed in the 18th century by Immanuel Kant and refined over the centuries. Our solar system would be born from the gravitational collapse of a small part of a nebula. Nebulae are giant molecular clouds. The largest part of the cloud would have formed the Sun, and the scattered remains around the Sun would have formed the protoplanetary disk. This disk, composed of gas and dust, then served as a basis for the formation of planets, moons, and asteroids. In each planetary system, there is what is called the ice line. You may also hear it referred to as the ice line, frost line, or snow line. Whatever you call it, this fictitious line is the boundary between which a given chemical species exists in solid form. In other words, before the line, the species is in the form of gas, and after the line in the form of ice. There is therefore one frost line per chemical species, although this term is generally used to refer to the ice line of water. In the outer solar system, i.e., beyond the planet Mars, planetary objects are born from a structure similar to a comet, i.e., a mixture of water and rocks. They are then less dense than rocky planets. Their composition depends on their position relative to the frost line. Planets and icy moons that form near the frost line contain mainly water and silicates. And planets that form further away may contain, in addition to ammonia, methane, carbon monoxide, nitrogen, and carbon dioxide CO2. As the protoplanetary disk dissipates, the planets that formed further inside the disk will tend to migrate closer to the Sun. Planets that formed in the outer regions and migrated inward are more likely to contain abundant water than planets that form near the star. A water-rich planet near its star was therefore formed farther away from the star before moving closer to it. The migration of icy planets to the interior of the star system involves the ice melting and becoming liquid, which transforms icy planets into oceanic planets. When a planet forms, much of the water in the planet is initially trapped in the mantle. As the planet cools, the mantle begins to solidify, and large amounts of water, between 60% and 99% of the total amount in the mantle, dissolves to form a vapor atmosphere. This atmosphere can condense to form an ocean. A heat source is therefore necessary to form an ocean. It can be, as you have seen, scientists are trying to establish models of the structure of an ocean planet once it is formed. The structure of an ocean planet depends on many factors and can be inferred from its density, shape, and gravitational pull. Studying an exoplanet can allow scientists to determine whether or not the celestial body has undergone differentiation, that is, separation into rock and ice layers. The small icy moons are made of a layer of water on a silicate core. In the case of Enceladus, the ocean is located between a solid shell of ice on the surface and the silicate core. Since the ocean is in direct contact with the silicates can provide hydrothermal and chemical energy to low-complexity life forms. But Ganymede, which is larger and contains more ice, has an even different and more complex structure. The pressures are high enough that there is an ocean between two ice shells. Imagine a sandwich with the ice instead of bread and the ocean as a filling. The filling of a sandwich is always composed of several elements or layers. This is also the case for Ganymede and the large ocean planets. As the pressure is variable at depth, water worlds may well have a structure that alternates phases of steam, liquid water, high-pressure ice, and plasma. Some of the water contained in ocean planets could take the form of Ice 7, a crystalline form of ice that is stable at high pressure. Let's stop for a minute to think about Ice 7, because it is a fascinating concept. This ice form was modeled by American physicist and Nobel Prize winner Percy Williams Bridgman in 1937. In 2017, it was observed directly in the form of inclusions present in diamonds mined at the Europa mine in Botswana. These diamonds were formed in the transition zone of the Earth's mantle between 410 and 660 kilometers, or 250 and 410 miles deep, as liquid water subjected to very high pressures and temperatures. When the diamonds were brought up, the liquid water crystallized because of the drop in temperature, the pressure remaining about the same due to the rigidity of the diamond. The ocean of water worlds, thus trapped between two layers of ice, could be maintained if the ratio between the speed of internal heating and the speed of evacuation of the heat is favorable. The heating by the tidal force is thus a criterion of choice in the study of the oceans of these aquatic worlds. The one does not go without the other. Astrophysicists who study ocean worlds must also take into account these characteristics to better understand their structure, since they cannot go there to make direct observations. Smaller ocean planets of less than 1 Earth mass would have, according to the models, a less dense atmosphere and a weaker gravity. Liquid water could thus evaporate more quickly. But liquid oceans could be fed by hydrothermal activity, or tides, for example. Once again, a fragile balance that all potentially aquatic planets may not be able to maintain over time. Let's now move closer to an ocean planet to see what its composition could be. If we take the example of our Earth, water covers 70.8% of the planet's surface, but represents only 0.05% of its mass. The Earth is therefore not what we call an oceanic world. This percentage is much higher in the case of an ocean planet. For example, in the case of TOI 1452b, the first potentially habitable ocean exoplanet discovered in 2022, liquid water would represent 30% of the planet's mass. Does it surprise you that the oceans of oceanic worlds represent such a high fraction of their mass? Actually, it's not that surprising. Models suggest that watery planets have oceans so deep and dense that even at high temperatures, the pressure would turn the water into ice, allowing a mantle of complex ice forms like V-ice to form. V-ice is not necessarily as cold as the ice you know on Earth. Yet another fascinating form of ice. For liquid water on the surface of an ocean planet to remain liquid for long periods of time, the planet must orbit in the habitable zone of its star, also called the Goldilocks zone. Its gravitational attraction must be able to maintain sufficient atmospheric pressure to retain the water so that it does not evaporate into space beyond its atmosphere. According to the models, a powerful planetary magnetosphere is needed to protect the atmosphere from mass loss due to stellar winds and to retain the water. Either the atmosphere of a planet is formed by outgassing during the formation of the planet, or it is captured gravitationally from the protoplanetary nebula. It is the greenhouse gases of the atmosphere that will govern the surface temperature of an exoplanet. Greenhouse gases will also absorb and redistribute energy from the star around which the ocean planet orbits, which can give valuable clues about the composition of the atmosphere. The composition of a watery exoplanet and its atmosphere depends, among other things, on its position relative to its star. If the planet is close enough to its star for the liquid water to reach its boiling point, the water would reach a supercritical state. We speak of a supercritical state when water is subjected to high temperatures and pressures, but not to the point of becoming solid. If the ocean planet is colder, then the atmosphere could be much thicker than that of the Earth, and composed largely of water vapor, which could produce a greenhouse effect. The planet would then have to be small enough or close enough to its star for the hydrogen and helium to be volatile. Otherwise, it would be the equivalent of an ice giant, like Uranus and Neptune, but hotter. Icy planets that have migrated to the interior closer to their star could develop thick vaporous atmospheres and thus retain their volatiles for billions of years, even in the event of atmospheric leakage. Atmospheric leakage is caused by ultraviolet radiation and leads to the erosion of the atmosphere, as well as the eventual loss of the oceans. Indeed, atmospheric leakage also means leakage of water vapor, and therefore leakage of hydrogen and oxygen into space. Models estimate that the amount of water lost is roughly proportional to the mass of the planet. You have understood that there is not only one model of atmosphere for the ocean planets. On the contrary, there are many possibilities. However, because a general model must be developed, scientists have estimated that the composition of the atmosphere of an icy planet that became an ocean planet would be about 90% water, 3% ammonia, and 5% carbon dioxide. Now that you have understood how ocean planets are formed and what these watery worlds look like, you are probably wondering if life can develop on them. Can life forms be found on these ocean planets? Or even better, an intelligent extraterrestrial civilization? Are ocean planets inhabited, like the Camino planet from Star Wars? The first thing to know is that if the planet is entirely covered with water on the surface, then the development of terrestrial life seems unlikely. And if there is a layer of solid, pressurized ice between the liquid water and the rocky mantle, the development of life as we know it is even less likely. Scientists have addressed this issue by studying hypothetical ocean worlds. In the case of an ocean planet covered with 5 terrestrial oceans of water, it would not contain enough phosphorus for terrestrial ocean organisms such as plankton to develop. Plankton is an oxygen producer and therefore plays a crucial role in the oceanic ecosystem on Earth. On Earth, phosphorus, which is essential for its development, reaches the oceans through rainwater that has hit the rocks of the land, a mechanism that could not work on a planet entirely covered by oceans. Another simulation investigated the hypothesis of an ocean world containing 50 terrestrial oceans of water. The pressure on the ocean floor would be so great that there would be no plate tectonics. Without plate tectonics, there is no volcanism. And without volcanism, there is no chemical environment for the development of life as we know it on Earth. However, these observations do not mean that there can be no life on ocean planets. Small ocean worlds like Europa and Enceladus are considered habitable environments because the oceans are in direct contact with the silicate core. Now, the silicate core is a potential source of heat and can also provide chemical elements that could be the origin of life. In addition, according to some researchers, the thick underground ice sheet could be a means of transport for some ingredients of biotic activity. According to a study published in the scientific journal Nature Communications in June 2022, there could be exchanges between the core and the ocean, despite the presence of a thick ice sheet. Until now, scientists thought that this ice, type 7, was too dense and prevented any contact between the ocean and the core. But finally, this ice is not so impermeable as we thought, and it could bring some chemical elements to the surface. In addition, in 2021, a bioscience study led by Jeffrey Dick and Everett Schock of Arizona State University showed that organisms can thrive on the seafloor without light. This would also be possible on other planets, and thus in ocean worlds. On Earth, life is possible through a mechanism called cellular respiration, which involves the intake of oxygen and the release of carbon dioxide. But this mechanism does not work in the ocean depths without heat or light. This does not mean that there is no life on the seafloor. The study has shown that at the bottom of the oceans there are some specific hydrothermal environments that can harbor complex organisms. This is the case, for example, of hydrothermal vents or hydrothermal mounts, vents located on the axis of oceanic ridges that were formed as a result of tectonic plate movements. Around these vents, hot fluids mix with very cold seawater, an environment that may seem extreme, but is nevertheless conducive to the development and life of tiny organisms. When the vents are composed of ultramafic rocks, magmatic rocks that are very low in silica and produce a lot of hydrogen, this is particularly favorable for the biosynthesis of the basic elements of cells, like amino acids and sugars. Even more energy is needed for a reaction called polymerization, which will create larger molecules such as proteins. This study shows that even in a particularly inhospitable ocean environment, life can be born and develop. This gives hope to scientists who believe that ocean planets could harbor an extraterrestrial life form. If it exists, life on an ocean planet would be very different from life in our terrestrial oceans. For one thing, the oceans themselves would not look anything like our own. The oceans of these aquatic planets would probably be subject to violent storms. Cyclones would form and suck water vapor over the oceans, and since they could not lose their strength over land, they would cause huge waves of several tens of meters high. If there was life in the oceans of the water worlds, then it would have developed rather in the depths, in a calmer zone, or else life would not be easy. Now that you have understood what an ocean planet is, and that you have had a glimpse of what such a planet would look like, we are going to take a trip to the heart of the most famous ocean planets. On this trip, we will go as far as 219 light-years away. You will be able to observe Gliese 1214b, the first ocean planet ever discovered, and TOI 1452b, a potentially habitable ocean planet, discovered in 2022. You'll also see K218b, the first exoplanet in the habitable zone where traces of water have been found. And we'll explore multi-planetary systems like TRAPPIST-1, Kepler-62, and Kepler-138, which host several planets, including ocean worlds. Fasten your seatbelt and take off for the watery worlds of our universe. Let's start with Gliese 1214b. This is the first ocean planet that was discovered by calculation on December 16, 2009. This super-Earth, located at 40 light-years from us, is in orbit around the star, Gliese 1214, in the constellation of Serpentarius. Its mass is 5.5 to 7.5 times that of the Earth, and its radius is 2.6 times that of our planet. Its average density is low, 2 grams per cubic centimeter. To give you an idea, the density of the Earth is 5.5 grams per cubic centimeter. This ocean planet would be, according to the estimates, composed to 75% of ice and to 25% of rock and metal. According to this hypothesis, the ocean of ice would be 13,000 kilometers, or 8,000 miles deep, and the rocky core would have a radius of 4,000 kilometers, or 2,500 miles. Close to its star, GJ 1214b would have a surface temperature of about 200 degrees Celsius, or 392 degrees Fahrenheit. Its atmosphere is 200 kilometers, or 125 miles thick, and would favor a greenhouse effect. The presence of life as we know it remains unlikely. Observations of this planet have been made by the Hubble telescope's Wide Field Camera 3, the most advanced instrument on board the telescope to take images in the visible spectrum. According to these observations, Gliese 1214b would be a largely gaseous planet, with a high amount of water in its atmosphere. The atmosphere of the planet would be composed of 50 to 85% of water molecules. But how was the presence of water in the atmosphere of Gliese 1214b revealed? In a 2018 study published in the Astrophysical Journal, Japanese scientists demonstrated that the planet's atmosphere did contain water using 2 optical cameras on the Subaru telescope on the island of Hawaii. the scientists waited for the planet to pass in front of its star to analyze the light passing through its atmosphere. For this analysis, they used the phenomenon of Rayleigh scattering, a light-scattering phenomenon that occurs when light particles are scattered without a change in wavelength. Installing a blue filter on the cameras of the Subaru telescope made it possible to determine the intensity of the Rayleigh scattering phenomenon. Since the scattering was weak, the scientists concluded that the atmosphere of Gliese 1214b is rich in water. But this conclusion must be refined because a weak Rayleigh scattering can also mean that the atmosphere is dominated by hydrogen and very cloudy. The observations also confirm that this ocean planet was initially formed far from its star, that it was rich in ice, and that it would then have migrated to approach Gliese 1214. Some of the water on this planet could be in the form of hot ice in an exotic state. The exotic state is one of the four possible states of matter, with a gaseous state, the liquid state, and the solid state. Or, water would form a supercritical ocean due to the temperature and pressure conditions. Supercritical water is obtained on Earth by heating water to temperatures above 374 degrees Celsius, or 705 degrees Fahrenheit, under a pressure of more than 221 bar. It is a powerful solvent for all organic compounds. If the oceans of Gliese 1214b were in a supercritical state, life would most likely not be able to develop there. Let's continue our exploration of the exoplanets most likely to be oceanic worlds. Located 100 light-years from Earth in the Dragon constellation, TOI 1452b is the most talked about oceanic exoplanet at the moment because it was discovered just recently, in June 2022. This exoplanet orbits a red dwarf star located in a binary system, which is smaller than the Sun. The two stars of this binary system are separated by 97 astronomical units, which is about 2.5 times the distance between the Sun and Pluto. TOI 1452b can be called a super-Earth because its mass would be equivalent to 4 to 5 times that of the Earth, and it would be 70% larger. TOI 1452b was discovered by an international team led by astronomers from the Université de Montréal. To discover this ocean planet so far from our planet, they used data from NASA's TESS Space Telescope. The main function of the TESS telescope is to observe the celestial vault in search of planetary systems close to our own. To do this, the telescope watches for minute decreases in brightness that are caused by the passage of a planet in front of its star. This passage is called a transit. The analyses of TOI 1452b estimate that 30% of its total mass would be water. The water could be in liquid form on the surface, since the planet orbits in the habitable zone of its star. Observations from the TESS telescope have also shown that TOI 1452b orbits its star in 11 days. To determine the mass of TOI 1452b, scientists observed the binary star system with a Spirou instrument that has been installed on the Canada-France-Hawaii telescope since 2018. The Spirou instrument consists of a high-precision spectropolarimeter and velocimeter and operates in the near infrared. The objective of this instrument is to locate exoplanets located in the habitable zone of their star, but also to observe the magnetic fields of protostars, i.e., stars that are only a few 100,000 years old. The goal is to finally unravel the mystery of how stars are born. Spiru measures the minute variations in the speed of stars that are caused by the planets orbiting them. With this instrument, researchers were able to estimate the mass of TOI 1452b at about 5 times that of the Earth. According to all the observations that have been made since the discovery of this exoplanet, TOI 1452b is probably a rocky planet, but with a density much lower than what we expect from a rocky planet like Earth. Observations that make scientists lean in favor of an ocean planet. According to them, TOI 1452b would even be one of the best candidates for the title of ocean planet discovered to date. Separated from the Sun by a relatively short distance on the scale of the universe, 100 light-years, TOI 1452b does not cease to interest astronomers. The James Webb Telescope, launched in December 2021, should help them to establish an even more precise portrait of this ocean planet. Let's continue our journey to the heart of the ocean planets of our universe. Located 40.5 light-years away in the constellation Aquarius, the TRAPPIST-1 system has fascinated astronomers since the discovery of 7 exoplanets around the red dwarf star, TRAPPIST-1a. Not only because 3 of these 7 planets are located in the habitable zone of the star, and are therefore likely to harbor life, but also because such a number of planets in the same system could tell us a lot about the formation of our own solar system. Compared to our solar system, the TRAPPIST-1 planetary system has even more rocky planets in the habitable zone of the star than we do. Our solar system contains 2, Earth and Mars, and TRAPPIST-1 contains 7. The star around which this multi-planetary system is organized is an ultra-cold red dwarf, which is much cooler than the Sun, although it is more massive. It has a diameter of 11.5% that of the Sun, and a mass of 8%. It contains much more metal than the Sun, 109% more, according to scientists, and it can live 400 to 500 times longer, up to 4 to 5 trillion years. TRAPPIST-1a will certainly be one of the last remaining stars when the universe will be so old that the gas necessary for the formation of stars will be exhausted, and that our Sun will have disappeared for a long time. TRAPPIST-1 was discovered in 1999 by astronomer John Gizis and his colleagues. 16 years later, the Belgian telescope TRAPPIST discovered 3 planets orbiting this star. By crossing the information provided by the TRAPPIST telescope and those of other telescopes, 4 other planets were then discovered. These are the planets TRAPPIST-1d and TRAPPIST-1e, which are most likely to contain water in the liquid state, according to astronomers. They are neither the 2 closest nor the 2 farthest from their star. They are in fact the middle planets. TRAPPIST-1b and TRAPPIST-1c are closer to the star, so much so that Planet B orbits TRAPPIST-1a in 1.5 days and Planet C in 2.42 days, or 58 hours. TRAPPIST-1d is the least massive planet of the TRAPPIST-1 system. It has a mass equivalent to 30% that of the Earth. It is also the one which presents the weakest density and the gravity of surface. Its surface temperature is 9 degrees Celsius, or 48 degrees Fahrenheit. To give you an idea, the Earth's surface temperature is 15 degrees Celsius, or 59 degrees Fahrenheit on average. Separated from its star by 2.2% of the distance between the Earth and the Sun, it receives only 4.3% more sunlight than the Earth. TRAPPIST-1d orbits around TRAPPIST-1a in about 97 hours, or a little more than 4 days. Like TRAPPIST-1d, TRAPPIST-1e is located in the habitable zone of the multiplanetary system TRAPPIST-1. This planet has many points in common with the Earth. Its mass, its radius, its density, and its surface gravity are approximately similar. The data collected show that its composition should also be similar to that of the Earth. Its average temperature is minus 27.1 degrees Celsius, or minus 16 degrees Fahrenheit, a little colder than Earth's. But since the planet is in synchronous rotation, it would be warmer in the part illuminated by its star, and water would be in liquid state, and on the contrary, colder in the unilluminated part, where it would be in solid state. So yes, the TRAPPIST-1 system has habitable planets, but can we observe ocean planets there? According to a 2018 study by Amy Barr, Vera Dobos, and Laszlo Kiss, TRAPPIST-1d could be covered with an ocean, while the outer planets, i.e. TRAPPIST-1f, G, and H, would be icy planets. However, because we have not been able to observe the TRAPPIST-1 system live, these remain guesses. Other studies show that according to their characteristics, and in particular their atmosphere, other planets of the TRAPPIST-1 system could be watery worlds. The planets F, G, and H could thus have an oceanic surface and a large core. TRAPPIST-1f is probably rocky, with a massive envelope of water vapor at very high pressure and temperature. It could therefore be covered by a thick ocean with an atmosphere rich in abiotic oxygen. Attention, it is not because there would be oxygen that it would be an indication of life. The abiotic oxygen comes in reality from sulfur dioxide. TRAPPIST-1g, the sixth planet of the multiplanetary system, certainly harbors water, since it is less dense but more massive than the Earth. If it has no atmosphere, it is surely an icy planet. But if it has a thick water vapor atmosphere, it could be an ocean planet. As its orbit varies little, it should offer a rather stable climate rather favorable to the development of an aquatic life form. TRAPPIST-1h, the seventh planet of the TRAPPIST-1 planetary system, is even more distant from its star. It could harbor a subsurface oxygen heated by tides. There would thus be on this planet a strong activity of cryovolcanism, with erupting geysers, as on the moons Europa and Enceladus. Let's move a little farther away from Earth to examine a planet called K2-18b, which is located 124 light-years from us in the constellation Leo. This planet, discovered by the Kepler Space Observatory in 2015, orbits the red dwarf star K2-18 in 33 days and is located in its habitable zone. However, scientists believe it is unlikely to be habitable. K2-18b is 8 times more massive than the Earth. It is a super-Earth or mini-Neptune. In 2019, 2 independent studies concluded by cross-referencing data from the Kepler, Spitzer, and Hubble space telescopes that the atmosphere of this planet would contain significant amounts of water vapor. The equilibrium temperature of the planet is estimated to be about -8 degrees Celsius, or 17 degrees Fahrenheit, and it receives 94% of the stellar illumination that the Earth receives. Based on its size and density, it is unlikely to be composed entirely of iron and silicates, so it could be composed of hydrogen, helium, and ice water. In 2019, analyses of Hubble data by researchers from the University of Montreal and University College London examined the spectra of starlight passing through the planet's atmosphere during transits and concluded that K2-18b has a hydrogen-helium atmosphere with a high concentration of water vapor, between 20 and 50%. The water vapor could be high enough to form clouds. K2-18b was the first super-Earth discovered in the habitable zone of a star with a detected atmosphere. It was also the first discovery of water in an exoplanet located in the habitable zone. As a result of these observations, scenarios have been developed to determine possible models for this exoplanet. Several of these models admit that K2-18b could be an ocean world covered with liquid water and with temperature and pressure conditions similar to Earth. We will know more with the observations of the James Webb Telescope, launched at the end of 2021, and the Space Telescope Ariel, developed by the European Space Agency, which should be launched in 2028. The star Kepler-62 is much more distant than TRAPPIST-1 or even K2-18b. Located in the constellation Lyrae, 1,200 light-years from Earth, it is an orange dwarf. At least 5 planets orbit it, including Kepler-62e and F, which are located in the star's habitable zone. In 2013, when they were discovered by the NASA Kepler Space Telescope, they were called the 2 most Earth-like planets ever discovered. Kepler-62e is a super-Earth, telluric like Earth, with a composition of iron and silicates. According to the hypothesis of scientists considered the most probable, it would contain an abundant quantity of water in addition to its rocky core. According to a modeling study of this planet, published in the Astrophysical Journal, it is likely that the planet is entirely covered by an ocean. Kepler-62f is the farthest planet from the star Kepler-62, so it is located in the outer part of its habitable zone. It is 1.4 times larger than the Earth, so it is also a super-Earth. It receives as much solar energy as Mars, and the year lasts 262 days on this planet. Like Kepler-62e, it would be one of the first 2 viable candidate planets as a habitable zone ocean planet. A University of California study led by astrophysicist Omawa Shields, and published in 2016, estimated that the temperature of this planet would be compatible with the presence of liquid water. However, for Kepler-62f to indeed harbor oceans, it must meet a few criteria. The planet would have to have an atmosphere 3 to 5 times thicker than Earth's, because its star heats less. This atmosphere, to maintain a temperature allowing the presence of water in a liquid state, should be composed largely of CO2. If, for example, the planet had an intense volcanic activity, it could maintain an atmosphere rich in carbon dioxide. And for it to be habitable, its atmosphere would have to be 3 to 5 times thicker than that of the Earth, as we have just seen. And in addition, the level of CO2 would have to be 2,500 times higher. What about the other planets in the Kepler-62 system? Astrophysicists have discovered 2 ocean planets, so they did not stop there. They investigated whether the other planets orbiting Kepler-62 could also be water worlds. Kepler-62b is the innermost planet in the multiplanetary system. It is about 30% larger in diameter than Earth and has an equilibrium temperature of 477 degrees Celsius, or 890 degrees Fahrenheit, which is slightly higher than that of Venus. No doubt, it is not an ocean planet. Kepler-62c is the second innermost planet after Planet B. It is about the size of Mars, but looks more like Mercury, the closest planet to the Sun in our solar system. It is therefore unlikely that this planet contains liquid water. Finally, Kepler-62d is not yet in the habitable zone, so it is too close to its star for water to remain in a liquid state. We end this journey with the planetary system Kepler-138. The star Kepler-138, or KOI 314, is a red dwarf star located in the Lyra constellation, 219 light-years from Earth. It is in the field of view of NASA's Kepler spacecraft, hence its name. In orbit around this star, 3 planets have been confirmed, and a 4th planet is likely. Kepler-138b is among the exoplanets whose size and mass have been measured, the one with the lowest mass. To give you an idea, the mass of Kepler-138b is similar to that of Mars. As for Kepler-138d, it has a very low density, so much so that it was long thought to be a gas dwarf planet, or mini-Neptune. A mini-Neptune is a planet whose mass is significantly less than that of Neptune, but which still shares some commonalities with this planet of our solar system. Mini-Neptunes have a thick atmosphere of hydrogen and helium over a deep mantle of water, ammonia, and other volatile compounds. If they did not have such a thick atmosphere, mini-Neptunes would actually be ocean planets. Recent studies from 2022 have shown that Kepler-138c and Kepler-138d are certainly watery worlds, with oceans 500 times deeper than those of Earth. They would also be warmer, with an atmosphere of hot water vapor. Let's go back for a moment to December 2022. Astronomers announced that they had identified the first true ocean planets, Kepler-138c and Kepler-138d. To reach this conclusion, astrophysicists compared the densities and masses of these planets with existing models And indeed, while these two planets are larger than the Earth, their density is nevertheless located between that of a rocky planet and that of a gas giant. To identify these oceanic worlds, astronomers use data from the Hubble and Spitzer space telescopes. The depth of the oceans of these two watery planets would be 500 times higher than the average of the terrestrial oceans. That is to say, a depth of at least 1,600 kilometers or 995 miles. Astrophysicists compared these two planets to Europa and Enceladus, except that Kepler-138c and Kepler-138d are larger and hotter than these oceanic moons. And instead of an icy surface, there would be large envelopes of water vapor. Kepler-138c and Kepler-138d constitute, for astrophysicists, the best evidence to date of the reality of oceanic planets, whose existence was theorized a long time ago. The oceans of these two planets would, however, be different from our terrestrial oceans. The available data show that they would be significantly warmer than our oceans, and that they would be under higher pressure. There may also be no clear boundary between the surface of the oceans and the atmosphere of Kepler-138c and Kepler-138d, which is certainly hot and composed of vapor. The temperature of this atmosphere is certainly above the boiling point of water. Under this hot atmosphere, there could be liquid water at high pressure, at depth, or in another phase like supercritical water. We have arrived at the end of this journey to the heart of the mysterious ocean planets. These aquatic worlds seem to come straight out of the imagination of a science fiction author. And yet, astrophysicists believe that it is more than likely that they really exist. What kind of creatures inhabit these extraterrestrial oceans? Are they microorganisms invisible to the naked eye? Huge prehistoric-looking creatures? Or ferocious creatures, like the Kraken of the fictional planet Mon Cala? Do these aquatic creatures have, as in our terrestrial oceans, a language to communicate between them? Do they inhabit the abysses of oceans more than 1,600 kilometers or more than 1,000 miles deep? Astrobiologists, astrophysicists, and astronomers are asking these questions and hope one day to be able to provide answers.